Oh, wow.
It's all messed up,
Yeah, yesterday was exciting.
Yeah.
So we were talking a little bit on different technologies for AI.
Cool.
So today we'll start using them.
Okay. All right. Good. Thanks for putting this together.
Of course. Yeah, thanks for support. Yeah. And first it says the unit for this. Of course, yeah. Of course, yeah.
Good morning, everyone, and welcome back. And just as we mentioned 10 minutes ago, we're going to start now. Again, people will trickle in. I think it was raining quite a bit, but suddenly it's not raining. So hopefully that allows people to come in before it starts raining again. It hardly rains here, so I don't know who brought the rain. I think it's the Pittsburgher. Because I lived in Pittsburgh for 8 years, and the question was, when will it not rain? And so it's great to see everyone. I just before I hand it to Dr. Ashkantala, my co-course director, and Dr. Vidula for Module 3, which I think will be very exciting, and more of the same, but more entrenchment of, hands-on. I want to make an introduction and also one announcement. Maybe the announcement first. You'll see from time to time, and you'll get an email about a survey. Before you leave, the survey should take, it could take 1 minute. There's only one mandatory question, which is the overall rating. It would take 30 seconds. But even if you fill out everything, it'll only take about 4 or 5 minutes or less, unless, there's some free text. It's up to you. Please fill it out, ideally before you leave, or as you're leaving on your ride share. And the second is, it's my great pleasure to just let everyone know that the APA, the American Pancreatic Association, of which I'm wearing the hat, and it says actually here, President 2026, because it was hand knitted by someone's daughter, and I want to introduce that individual. We have a robust board that's so dedicated to the mission. And Dr. Min Lee is the international liaison on the APA board, former president, and has many distinguished accolades in pancreatology, pancreatic cancer, at his home institution. He was in China, not, I think, at a distance from Shanghai, came, especially for this APA meeting, came from Shanghai to LA, got stuck in LA, I think, overnight, and is here just for a few hours to show his presence and to show the support of the APA. So I'd like to welcome Dr. Min Lee. And would you like to say? Okay, well, he's such a humble character. And so please, now I'd like to pass off to Dr. Ashkantala. Thank you.
Thank you, Dr. Hussain, and thanks everyone for joining Module 3. And as I was mentioning previously, yesterday you saw the Stanford team who did a brilliant job showcasing all the different AI tools that are available that could be used for research and in clinical practice. And today we will see more from the East Coast people, from the Hopkins side, we will see if these AI tools stand to the scientific rigor and how appropriately to use them, more from a pancreatology perspective. It's my pleasure to welcome Dr. Vedula, who will be directing this module. He is a surgeon by background who turned into an epidemiologist, statistician, then into a computer scientist. So now he's a full-time computer scientist between the School of Medicine, Engineering, and Public Health, and a great asset for us in the pancreas research. So we will together run this module and showcase a variety of exercises that we can work on. And as a reminder, please go to your Google Drive, Module 3, download all the documents. There are some links in there, some things you can play around as well online. So this will be an exciting module.
Thanks, Venkat. So a quick overview of what are we going to do today. Yesterday, you had access to a bunch of hands-on tools, and that was super cool. And I learned a lot myself. I was thinking last night, I probably learned more than what we're going to teach you today, but don't tell the president and the AP about that. So what we're going to do, what we're going to do today is use those tools more and more, but connect that with applications that you would do, that you would see in clinic, and connect it with concepts that you already know and ideas that you need to know to be able to work in the space of AI and pancreas care. So in activity, we have 3 activities. Venkat is going to break the ice first, and then we're going to spend a lot of time to put things together about how do we use all of this AI in either research or patient care in care of patients with pancreas disorders. And then in activity 3 is, we think of it as a capstone. You're going to be a decision maker in an institution where you're deciding whether an AI tool is ready for the clinic. And we'll lean on Venkat's work, Venkat's research to use that as a tool, and it'll be a capstone, another hands-on exercise. Handing it off back to Venkat to break the ice.
All right, activity 1. So we are trying to set up this stage, and we want you to think about where would you like to see AI in your practice. So in each of your table, try to think among your group, think among yourself, and you can use any of these tools that you have seen yesterday. Any of the LLMs, the Claude, ChatGPT, Gemini, Copilot, Notebook LLM, or any of these, whatever you like, and list one clinical problem in pancreatology that you believe AI should solve. And list the sources or types of data you think AI should use to solve this clinical problem. So take 5 minutes from your experience in clinic or research involvement or anything that you came across. Think of this question. If you want to take the help of an LLM, any of these, please go ahead. And you should also ask it what the sources or types of data you think AI should use to solve this clinical problem. And yesterday, you saw the prompt engineering from the Stanford group, the CoStar format. This is their slide. And you can use this format to run the prompt. So I will leave this on the screen. And let's take 5 minutes. And then each of your tables will just have 1 minute to explain your question. Super brief, to the point, what you came across as a group.
I just want to verify whether you're able to. We got a little behind with it. Everything's. They're more comfortable clinical.
I think. So,
Hybrid.
Hopefully you were all able to come up with good questions. You have 1 more minute, then we'll start picking tables. All right, let's see what you came up with. So again, the exercise was for you to come up with one clinical problem that you want AI to solve in the pancreatology world. You saw how powerful AI could be yesterday. So let's see what our group came up with. We'll start with table 3 and we'll go in order. So there are microphones going around. So please only speak in the microphone because we are recording. Table 3. Can you please tell us what was the question? What is the question in clinical pancreatology or in pancreatic disorders that you want AI to solve, and what type of data?
This is Shiro Rama, UC Davis. We were considering the as a clinical problem management of pancreatic cyst patient. There's a lot of many guidelines and a lot of issues that we have problem with every single year when they come up with another new guidelines. So I think that's one of the things that could have the AI.
Great. Pancreatic management. What type of data do you think you need to use?
The types of data, the source of types that you think I should use. Let's see, the source of type of data, the actual information. Yeah, that we have to obviously gather from.
Sure. Is it imaging? Is it some biomarkers you think?
Yes, it will be imaging, and certainly that various, the biomarkers that has not been validated, but it can be tested for further identification, potential, use for further research.
Great start. Yeah, we'll talk more about it. Next, coming to table 1. What is the clinical question you want AI to solve?
Somebody who knows something about pancreatology.
Anything you saw yesterday.
Did you find things? So our question, our question was thinking about, in cases of acute pancreatitis in adults, thinking about ways to figure out, to predict in some way whether they're going to become somebody with a recurrent pancreatitis or eventually chronic pancreatitis, and so really developing some sort of prediction model.
Great. Yeah, and what type of data do you think we need for that?
And we found, There may be some. Thank you.
So attack characteristics, etiology data, genetic variants, longitudinal imaging, exocrine function trajectory, endocrine function trajectory, patient-reported pain burden and quality of life over time, healthcare utilization patterns, and then, yeah.
Variety of data variables. Thank you. Table 4. What is the clinical question and what type of data? If you have to pick one.
So the clinical question is the diagnosis of chronic pancreatitis in pediatric patients presenting with abdominal pain. And the clinical data, we are essentially going to ask it to look at current guidelines as well as other sort of studies that may suggest what is chronic pancreatitis versus what is not. So it's an evolving project in our heads.
Great. And again, going back into what type of data, Swarup, you have any comments on what type of data?
We've heard a variety of patient-related observations. We've heard about imaging. So all data is good. We just want to make sure, we just want it to emerge from what your thoughts are.
Yeah, and the prompt includes clinical presentation, laboratory findings, imaging findings, all of the above. I mean, we can get more specific, CT, MRI. I mean, I think we could keep breaking it down if that's the idea.
That's excellent. Thank you.
Thanks.
Okay, next, table 5, the clinical question and the type of data.
So our clinical question is twofold. One is we asked to identify the risk factors for development of chronic pancreatitis after the first episode of acute pancreatitis based upon the guidelines and the data that we already have. And we used Claude and also ChatGPT for that. And it gave us the patient demographics, and the higher the score is, the higher the number, the higher the risk of developing chronic pancreatitis in these patients with the first episode of acute pancreatitis. After that, we asked to develop a easy to use score, such as like a ransom criteria. So then it gave us an APC 8 score based upon all the variables. And next step is to develop a website or an app where you can use these variables, plug it in, and we have the total score. So the higher the score, the higher the risk of developing chronic pancreatitis in these patients. So it already developed a web page app. So I'm going to download it and see how we can use it.
Wow, so you went through multiple steps.
Super. What you've actually shown is using LLM to solve that problem. But what we'll spend in the rest of this session is what are the other AI? So what are the other AI that's out there, and how can you use to solve problems that you want to see solved? But thank you. That was great. That was great.
Okay. Next, table 8, please. What is the clinical question and what type of data? Table 8.
We were looking at the question about for a patient who actually needs surgery, what kind of how to decide if the patient might develop complications, etc. So it's mainly for LM to see what's the treatment planning for surgical care. And it suggests to support decision on resectability, optimal timing, and the type of a surgery that needs to be done, and the risk of post-op complications such as the pancreatic fistula or bleeding. And the data it will be using to feed the model is the CT imagings, MRI, if any, and also using the different machine learning algorithms to get a prediction of what's the complication might be.
Nice, very well framed. And we'll go more in the exercises today, how to think about nuances for the type of data that you mentioned. Let's go to table 7, please, the clinical question and the type of data you need.
So my name is Garrick. I'm a PhD student at the University of Florida. The clinical question that we wanted to solve is early detection of pancreatic cancer, which of course is a pretty complicated question, but for the data, I think that a general model that predicts lifetime risk for the general population will probably have the most benefit. And as a specific data source, probably electronic medical records or some composite of available data, because a lot of patients just have missing variables, and that affects the trajectory of the risk.
Great. You brought up some important points on the missing data. So we will do more exercises on each of those, and we can talk about some of the methods to fix that. Okay. Now with the last table, table 6. What is the clinical question you want AI to solve, and what type of data?
Hey there, I'm Andrew Lehman, pediatric pancreatologist at Stanford Children's. I think one thing for us is in pediatrics, when it comes to imaging, is that volumetric measurements and response to secretin there's a lot of inter-rater variability and some variation in how these studies are interpreted. So I think using AI to get radiographic data and come up with more standardized ways to measure this, and also then to correlate it with its clinical outcomes.
Great. So we saw a variety of themes here in the pancreatology. So if we have a wish list of solving all of these, so these are some of the important questions we come across in the clinical practice: acute pancreatitis prognostication, chronic pancreatitis prognostication, identifying pancreas cancer early, pancreas cyst management, pancreas surgical candidacy and the prognosis after pancreas surgery, and so on. So we will briefly look into what else is being used in AI in the gastroenterology world. So as many of you in the clinical practice might have seen this revolution of AI applications in colonoscopy, which was the first tangible thing that we started seeing where AI could be used. So this is where AI could be used in colon polyp detection. It uses a variety of data components in computer vision, especially finding colon polyp. Then it started telling us what type of polyp it is, so we could manage it appropriately. And that led to further explosion of applications in other endoscopy practices, like such as in Barrett's recognition and classifying the type of Barrett's. On the right side, it's a bile duct stricture. Is it a benign stricture or is it a malignant stricture? More and more studies started coming up, and they were comparing with standard of care, such as with biopsies and other modalities, and showing that there is some impact on clinical care. We will go into each of those examples, and then we will talk about how clinicians and engineers talk to each other, how we bring up the clinical question, and how engineers suggest about how to solve these problems. And to show you a few other dimensions, we also started seeing some other applications like ambient AI in the clinical note dictation, maybe even in endoscopy note dictation. These are things that affect each of us. We spend hours every day in writing notes. How AI could potentially help us in writing these notes for us and making our lives easier, and also in resource utilization, resource management, and so on. And in today's theme, we will focus a lot about clinical decision making. Conventionally, clinician uses their own knowledge, their experiences, and guidelines to come up with how to manage each patient. For example, this is a guideline that talks about when a patient comes with abdominal pain and high liver labs, high LFTs. How do I make my decision about predicting the probability of there being a stone in the bile duct? And how do I manage this patient? Should I send the patient to surgery? Should I send the patient to ERCP? Or should I send the patient to EUS? Variety of decisions that come up. And conventional guidelines put patients in these boxes, in those silos. But in real world, that's not the case. There are so much interaction between those variables. So, and it is very hard to put those patients in those boxes, and that limits the accuracy. As you can see here, the accuracy using the conventional guidelines is 70 to 75%. So around 13 to 24%, we do unnecessary ERCPs. That has its own complications. So here we talk about how AI could potentially be used in coming up with prediction models, in decision-making tools. where you can put a lot more data in, and where AI could look into the interaction between these variables and come up with more accurate prediction. Here, these are a bunch of variables that we were able to put in to come up with a prediction model to predict the probability of cholelocholithiasis, or the bile duct stone. Then it also tells us which modality would be the most appropriate, and it compares with the conventional guidelines. So this will be an important theme for the exercises today in coming up with prediction models. And now, very briefly, switching to potential pancreas applications, very similar to what many of you have said. So one application that looks at potentially some computer vision based data is, this is on the left side, you see an ERCP being done. This is an expert endoscopist, but you can see still getting into the bile duct, understanding the anatomy of the bile duct, understanding the direction of the bile duct is often pretty challenging. So AI could help level the playing field for all the endoscopists that can guide us and give us a roadmap on which direction we should be going. And throughout the day, you will see how these all tools will come together. And one important application we keep hearing about is rapid on-site cytopathology. When we do endoscopy biopsies, we look at the slides. Sometimes it is not very sophisticated. We don't need a cytopathologist to be in the room. AI could potentially help us understand, is this biopsy enough? What type of biopsy this is? So we can avoid the need for an in-person being there. And today, some of you have brought up the theme about pancreas cancer early detection. So for me to detect pancreas cancer early and give the information to AI, I need to first train AI and showcase whether it is a CT of the pancreas or endoscopy ultrasound of the pancreas and so on. I need to give it the information and train it appropriately. So these are some examples of segmentation or delineating where the pancreas is. As you can see, AI is able to identify where the pancreas is on the top left video, on an endoscopy ultrasound. And on the right side, AI is able to find the pancreas mass and give us the probability of it being a malignant lesion. And on the bottom slides, you can see AI could potentially differentiate between benign and malignant lesions in the pancreas. So these are all stepwise. But one pie in the sky question for us is, can we detect microscopic lesions in the pancreas before it becomes macroscopic and visual pancreas lesion? So which are PANINs, which are microscopic pancreas cancer precursors. Majority of the pancreas cancer, like around 80% of pancreas cancer, comes from PANIN. So those are microscopic, so how can I see on CT or ultrasound or so on? But they create some changes in the tumor microenvironment. Those are potentially some of the things that we can see on maybe the endoscopy ultrasound. So as you can see on the example here, on the left side, top, you can see an endoscopy ultrasound of a patient. These are some black spots. I have no idea what those black spots mean. It could mean pancreas cancer precursor lesions, or it could just mean fibrosis. So it is very hard for me to decide sending a patient to surgery because these are big deal surgeries. This patient was eventually sent to surgery. On the bottom, on the left side, you can see from the same part of the pancreas, there are small pancreas cancer high-grade precursor lesions. So this patient's life was saved because this patient was sent to surgery. But we could also be mistaken. This could be just fibrosis. This could be just benign changes, and it might have been unnecessary surgery. So the theme here is we have to teach AI with lots and lots of data and give it enough ground truth and create the delineation around the pancreas if necessary and show this is pancreas, this is variety of pancreas, this is benign pancreas, this is malignant pancreas, and so on. So it takes a lot of data to teach AI, and that is something that you will see today. And some of the other theme that came up today is prognostication in acute pancreatitis, chronic pancreatitis. How would it transform into acute pancreatitis severity prediction? We did a systematic review, and we saw in the last 3 years, there were 30 different prediction models that were developed by different groups from a variety of countries. All of them had very high AUC, 0.91. And none of them validated a different model. Everybody came up with a new model. Everybody used a different LLM or whatever it was in coming up with prediction models. And on the right side, you can see some quality assessment tools of these prediction models. You can see so much red. There were so many deficiencies in those prediction models. So that is the reason they did not end up in practice. So one of the theme for today's exercise is talking about quality, how to do it appropriately. how to assess if your AI is right fit for your patient, and so on. So this is how we are trying to set up the stage and go into activity 2. Swaroop.
Thanks, Venkat. So what we've seen is you can solve a wide variety of clinical problems with AI tools. When we say tools, these are not tools like what we used yesterday. These are tools that are developed with machine learning and engineering techniques. In this activity, it is going to be a dynamic to and fro. We want to lead you through a bunch of sequential activities. For each activity, you get 5 minutes to do. The Google Doc folder has a Word document with instructions for each activity, one at a time. You get 5 minutes to follow the instructions and do that, and then we debrief with you for 5 minutes. These are the learning objectives. This is what we are aiming to create a learning environment for. We want to make sure, we want to see if we can differentiate between well-designed and poorly designed research questions. We've listed a ton of research questions, but how do you ask a research question? And we're saying, let's use the tools we used yesterday to figure that out. And can you evaluate whether the data is ready for AI? Yeah, Venkat just said we need lots of data, but when do we know that the data is ready to develop AI? And the third is, what are the different types of AI methods, and how do we understand the relevance to pancreas conditions? Finally, how do we analyze AI research for its with critical thinking skills? So we'll go to activity 2A. You're going to the document that says 2A.
And please download the manuscripts from the Google Drive. So this is the paper number 1 in the Google Drive, the Barrett's prediction model. So to set up the clinical context, so there are many of you who are endoscopists. So I will pick up on a few endoscopists, and I'll ask some question on how they manage patients with Barrett's disease. This is not exactly pancreas, so Barrett's disease, some of you I'm sure still do Barrett's ablation. So you have seen a patient with Barrett's disease, a precancerous condition in esophagus, and you want to prevent this from turning into cancer. So you have done a procedure called ablation to burn the Barrett's esophagus to prevent it from turning into cancer. You have done so many sessions to slowly burn it all off, and then you are happy with it. But you are a little worried that the Barrett's might come back. That was shown in variety of data that the Barrett's might come back. How do I do surveillance for this patient? When do I bring the patient back? At what interval should I do the surveillance? So let me pull up some of the endoscopists here. Dr. Arain, so how would you manage a patient after you have completed your Barrett's ablation? Microphones for you, please.
So I think it depends on the pre-ablation diagnosis as well. So if it's low grade, which is questionable to begin with, you may wait 6 months. And if it's high grade, you'll come back at 3 months. And if it's intramucosal cancer, then 3 months usually. So, and then you're looking for other factors, whether there's any other high-risk features before ablation.
Great. There are so many variables that go into our thinking. Yeah. And it's from mentally, it's a hard exercise to do to predict like when you should bring the patient back. And now each individual endoscopist might have a different experience and perspective. And guidelines are also not very rigorous on this. Yes. So that is the reason this exercise is on predicting when to bring the patient back using a large volume of international multi-center data.
So going over what you're doing, you have a paper in the Google folder called Paper 1, Barrett's. You are uploading that paper. Yesterday you used Notebook LM. So create a new notebook in Notebook LM, upload that PDF file to Notebook LM, and you're interrogating you're using Notebook LM to interrogate that paper and saying, what is the research question addressed by that research paper?
There is a sample prompt given in the document, and the teaching assistants can help you out to run that prompt in the Notebook LM.
if you open this document through the Google Drive, you should be able to copy this sample prompt and paste it into Notebook LM. You're looking for Module 3, the folder for Module 3. The Word document. Okay. You're able to find things. Shall we start debriefing? If we look at the research question, there are multiple components in a research question. Many of you raised what are the problems to solve that AI should be solving in pancreas conditions. When we think through the research questions for a research study, taking this as an example, these are prospective longitudinal studies. The first item in a research question is who are the participants? Would anyone like to say what your Notebook LM interrogation said about who the participants are?
Looks like the return was the population was 2,511 patients with BE-related neoplasia.
Any more detail anyone would like to add? So when you think about yeah, please go on.
Looks like it says in patients who have achieved complete eradication of intestinal metaplasia following endoscopic eradication therapy.
And any exclusion criteria? Any patients who are not eligible?
Non-dysplastic Barrett's esophagus.
How did you find the Notebook LM? Was it giving accurate information?
Yes.
Yeah. And then this is an evaluation of a prediction tool. So we think of it as a test. You have some information, you're using it to test what will happen to patients in the future. So we think the second component of that research question is, what is the index test? Did you try can anyone say what Notebook LM said about the index test part of the research question? So the index test is really the prediction model. So the prediction model that they developed. And the C in a research question is the comparator. With a prediction model, the comparator is always the ground truth. Okay, did you see what a Notebook LM gave out for what is the ground truth? Or what were they evaluating the model against? The clinical diagnosis? Still thinking. I'm sure you would have seen these research papers and went through this activity manually in the past.
Swaroop, if I have these AI tools, so as I'm designing this question and trying to use these AI-based prediction models, how do I frame my picots?
You're thinking about who are the participants you want to use this model in the clinic, and that's what you would see. You would define your inclusion criteria and exclusion criteria to match the patients in whom you would use this in the clinic. The index test is always the new test that you're developing. In this case, the prediction model that you're seeing on the screen. The comparator, you can either compare it with a previous model or maybe something like the Ranson's criteria. In the case of this paper, the outcome is the ground truth, or we call it the gold standard. We call it reference standard, different names. In this case, it's with the T in the research question is the time horizon. If you interrogate this paper with Notebook LM for what time period and what's time horizon, it should say 1 year, 3 years, and 5 years. Because they predicted their patient's outcomes at 1 year, 3 years, and 5 years. And the last is a setting in which you use the prediction model. In this case, this is tertiary care hospitals or yeah. So that's the breakdown you do. So what we wanted you to do in this sub-activity is you already know many of the things, many of the concepts we talked. How do you build a research question? You already know that. Using a notebook LM to interrogate that paper with more specificity. You could have asked notebook LM, do a critical appraisal of this paper, but that wouldn't help. If you want specific information out of the paper, this activity is supposed to get you through that experience.
So what if I am not a developer, but I'm a clinician? I saw this manuscript in the journal, and I want to see if I can use this in my patient. So how do I think and how do I use Notebook LM to evaluate if I can use this information in my patient?
That's a good question. Before I say something, would any of you want to respond? Which is what you did just now. You took a LM and you said, I have this patient in front of me, and I'm deciding whether to use this model in my patient. And you say, you interrogate the paper for these PICOT conditions, and you say, I want to understand I want to get the risk of this patient developing this outcome 1 year from now. Did the patient answer that question? Did the paper answer that question? And what you've seen through this exercise now is, yes, it answered that question. But are the participants in this paper, in this predicted model, do they match my patient? Is my patient similar to the patients in the paper, in the study? And that is this interrogation is what would give you the information you need to make a decision as a clinician, to say whether this evidence whether this paper and the evidence in the paper is applicable to what you want to do now.
I think that's a good segue to activity 2B.
Yes. So this is exactly what you're doing in activity 2B. You're going into more detail and interrogating the paper, the same paper, so same notebook in Notebook LM. Now, if you look at the sample prompt for 2B, you're interrogating it for what are the specific inclusion and exclusion criteria that was specified in that paper. The sample prompt in the Word document, see how it looks and revise it, improve it, change it as you see fit.
So you can use the sample prompt to ask the question on inclusion and exclusion criteria for the patients in this manuscript. And then you can better understand if these patients fit your patient profile. And anybody want to volunteer and describe what Notebook LM said? Yes.
So I just want to comment that the two of you are going at 10 times the speed that we can possibly function. So if you can somehow slow this down, and I'm speaking as a clinician here, so because this exercise is great, but the methodology of the exercise is what we're struggling with. So I know we have time limitations. Regardless, the inclusion criteria are confirmed neoplasia, treatment completion, and achieved CEIM. And the exclusion criteria, non-dysplastic Barrett's, missing outcome data, and no follow-up. That's what this tool gave us.
Did you fade out?
Yeah, I think so. I mean, that's because they want indefinite for dysplasia, low-grade dysplasia, high-grade dysplasia. So all the high-risk lesions, right?
Great. Thank you very much. And thanks for the feedback. We'll go slow. Anyone else wants to comment, question, chime in before we? Okay.
So this is very simplistic, I think, but one of the things I asked Nobel LM is I said, okay, tell me about the limitations of this paper. And it laid out several ideas and then and gave me a basis for going back and looking carefully at the article and saying, okay, that makes sense. I think that is a limitation that's built into this paper. So anyway, I thought that was kind of a simple-minded approach that was actually better than expected.
Yeah. Yeah, great, thank you. Yeah, I did the same with this one. This is actually a good tool. It seems like it's not making that many mistakes. So I want to draw your attention to the screen for a second. Why are we talking about inclusion and exclusion criteria? So I want to share this with all of you because this is the framework with which I keep things coherent in my mind. What happens, this is how things work out. We have a population of patients. We want to use a prediction model in patients with certain characteristics to make a clinical decision. That's the population of patients. We take a sample of those patients. We have a hypothesis that if you use these kinds of data, you can predict outcome at 1 year with some level of accuracy. And we collect data. We've heard a variety of data that all of you described today. The benefit of AI is you're not limited to tabular clinical data from the electronic health record. You can work with many complex data. So you collect data from the sample, you build your AI model, and you test it. That's what we are seeing as the algorithm development part of this framework. Once you do that internal validation, then you have external validation, and then you say, if I use this in my patients prospectively, how wrong will I be? What are my patient outcomes? So that's the patient care part of it, translation to patient care, evaluating its impact on patient care. And then finally, the last part of it is, if you let this AI model go loose into clinical practice, what's the impact it will have on the society? So this is a framework in which I keep things coherent in my mind. If you think of any prediction model, it could be any of the prediction models that you talked about today. They'll all fit in this framework. So I wanted to share that with you so you can take this home with you. These are the questions. Most of the questions all of you asked, they are in this framework. Is this algorithm valid? Which is what we're looking at this Barrett's paper. Is it valid? Is the algorithm, what's the sensitivity specificity for this algorithm? Does the algorithm have clinical efficacy? Which is what we ask when we say, what happens when we use it in patients? And what's the clinical effect of clinical use on patient outcomes? Do patients have better outcomes if this algorithm is used in clinical practice? And the societal impact. This has saved me a lot of acid burn, so heartburn, so I thought this would be something cool for you to take home. We could switch to activity 2C. Do you feel ready to? Okay. So activity 2C, again, the same workflow. The Word document has the instructions. It has a sample prompt. You're interrogating but this time you have 2 more papers. So you're working with 3 papers this time. The remaining 2, one of the papers is the Barrett's paper that you just did. The remaining 2 papers, the PDF files, are in the Google folder for module 3. So you're uploading, you're working with 1 paper at a time. You upload the paper to Notebook LM. So this time maybe you find it better to create a new notebook because you're adding the other 2 papers as well. Create a new notebook in Notebook LM. Upload 1 paper at a time. And you're asking a very simple question. What is the machine learning or AI model that was developed or evaluated in this paper? Good?
Yeah, the TS can also help out in uploading all the documents and preparing a new Notebook LM.
some extra copies here.
As librarians, how did you like the papers we picked?
How do we like the what?
The manuscripts we picked, we tried to pick some different tradition
Well, for
models.
me, I have an art history background, so it's somewhat terrifying.
That's right.
All I know is like,
Pictures of pancreas.
right, is I don't have various
No.
let's rally together again.
So the activity 2C discussion, Swaroop.
So let's see, these are the models from these papers. Do you see the same answers from Notebook LM when you say, what is the machine learning or AI model developed in this paper? For Barrett's, there are two of them, random forest and a Cox proportional hazards regression. And for paper 2, there is something called a segment anything model that was fine-tuned furthermore in that work. And for paper 3, there is a mask RCNN, which is a convolutional neural network, and a model called YOLO V8. Engineers, they like their acronyms, and so they try to have fun with their acronyms. In this case, it's not you only live once, it's actually you only look once. But an interesting anecdote about Cox proportional hazards regression model. So I did my PhD in epidemiology, and I learned some statistics, and I learned logistic regression as part of statistics training. So I go to engineering for my postdoc, computer science, and there is this PhD student said, hey, I did a machine learning model to predict something. I said, okay, talk to me, I'm curious. She said, I used logistic regression, I used these inputs, I predicted this outcome. I said, wait, logistic regression is not machine learning, it is statistics, it's biostatistics. She said, nope, machine learning. What do you think? Is regression a machine learning technique or a statistics technique? Both. So surely enough, she said, I will teach you something today. So she brought the Machine Learning 101 textbook by Bishop, and she took the first chapter. Sure enough, there it is, logistic regression. What I learned that day is that in statistics, we think of regression as a model with some coefficients, right? Each variable gets a coefficient. So you estimate those weights. You say, what are the weights that will give you the best fit model to the data set? That is how we think about a regression model in statistics. Engineers say that model is a function. Y equals ax plus b, it's a function. This machine learning and AI models just happen to be just more complex functions, but each model is a function. My job is to find the best function that will take the input and give me the correct output. So they didn't think of it as a best fit model to the data, they think of it as the best function. It's a different in perspective, but Cox, we can also think of Cox as a machine learning model. It's a regression model. Good? So you had a chance to interrogate, and I hope you had a chance to explore Notebook LM with these papers as well. There is actually evidence that when you learn by exploration, you learn faster and you learn more. It's a paper in Science. So I hope you had a chance to explore. But I'm also expecting that you would begin to connect with these kinds of names of these models. Because when you go back, you will engage in one form or another with research that involves AI methods, research that involves this complex data. So I'm expecting that you're beginning to connect with these terminologies. A CNN, a convolutional neural network. A segment anything model is a foundation model. So that's another terminology I wanted to introduce. It was built by Meta and released publicly. Like the name says, it segments anything. You give it an image with people in there or some objects in there. That foundation model can draw masks, can outline each object in that image, every object in that image. Venkat showed earlier an outline around the pancreas in the ultrasound image. That's what a segment anything model can do. It'll outline objects in an image. Meta has come out with an advanced version of SAM2. It's a foundation model. Would someone like to chime in and say, what is a foundation model? If no hands, then I'll say. I don't want to talk too much. So, Okay, a foundation model is, it is trained with humongous amounts of data. Segment anything model was trained with millions, dozens or hundreds of millions of images. It is not trained to do anything specific. GPT is a foundation model. Cloud is a foundation model. They are not trained to solve one specific problem. They are trained to learn information in the data so that you can repurpose it. So segment anything model was trained in that way, and we can repurpose it to segment the EUS, the pancreas and the EUS images, for example.
Swaroop, so many of our members here are interested in detecting pancreas cancer early, as you have seen. So I want to give the tons of data that we have of patients pre-diagnosis. I have their CT scans, EUS, and so on. And I want to train AI and help me find cancer early, maybe those tiny microscope lesions. So that has been the theme here. So can I use these SAMs to feed all this data if it was not pre-trained on EUS?
Yes and no. SAM, at least SAM was not, it was trained with numerous images, but there were very little images from CT scans or MRI. There were a smaller number of medical images. So when it was learning information, it did not see many medical images. So what you do then is you take SAM, you take a small data set of CT images from your data set, you draw the ground truth manually in your data set, you take SAM and you tell SAM, I want you to adapt to and learn from my data set to solve my problem. And you can do that. That's fine-tuning or adaptation. You can do that. Sorry. Yeah.
So this is all done post-procedure, patient's gone, we're analyzing. Is there a potential for integration in real time, especially with EUS, if you have a model that's already learned from previous EUS?
And so those are great points. This is not an academic exercise just to build a model, but I want to use it in my patient real time during the endoscopy procedure. Swaroop, how do I do that? Because I don't want it to be just a publication. I want to be able to use it in patient.
You come to me, we write a grant together, and we solve it. We build that model. But the idea is that people are doing it, both for EUS and for other surgical videos as well, and endoscopic videos as well. We've seen endoscopic colon detection as the procedure is happening. What's happening, if we break it down into what exactly is happening, there is this video, EUS video frames coming into the system, into your computer from the probe, images coming at 30 frames per second. You need your network to analyze every image, do the segmentation in every image, and be able to show you with very short latency, which means very quickly do that segmentation, show it to me on the screen, so that I get information on what I'm seeing in my ES video. The challenges there are to build the model that can segment it correctly. And the second challenge is how do you give the information back to the surgeon so quickly that it's actually useful to you. Thank you for bringing that up, because that is a superb concept that is necessary to close the loop. I wanted to put all of this into context. Why are we asking you to do these activities in activity 2, 2A to 2B, 2F? Why are we asking you to do that? So the bigger picture context is that we are here because we see potential for AI making our lives easier on a daily basis, that we don't have to spend 3 hours creating a slide deck out of a paper. But we are also here because we see a lot of clinical potential for AI. That potential was evident since the 1950s. Soon after AI methods began developing, people saw potential for AI. And there were multiple previous applications in computer-assisted diagnosis and so on. December 2025, FDA has already cleared 1,430 AI-enabled devices. The Barrett's model that we are seeing in paper 1, that is an example of a model that can be translated into a decision support tool. But then, what is AI? We've heard of it a lot. Large language models is a tiny sliver of AI. It's a very tiny sliver. It's having a huge impact on our lives, but it's a tiny sliver. Those models were built by methods called deep learning, and deep learning is a subset of the space of methods in AI. And machine learning, deep learning is also a type of machine learning, and machine learning is a subset of AI methods. There are other AI methods. In fact, one of the pioneers of AI is at Stanford here. There are many other AI methods that are out there. We can use them. We don't use them because we're not familiar with them yet. But this is the space in which we're talking about things. LLMs, if you imagine a dot in the deep learning ellipse, LLMs are that dot. Large language models are that dot. There's so much more there. We've talked about, there are a few concepts I want to make sure you connect here, because you'll see those in your papers, and you'll see those in your work in the future if you engage in this space. What does a machine learning algorithm do? Like I was saying earlier with my anecdote on statistics, we have data, and in this case, the data happen to be images of showing a number, and we have the labels, which is the ground truth, and this is the data we use for training. This is a very simple cartoon example. But you listed many types of data, complex data, CT, MRI, patient-reported outcomes, time series data, so on. All of those can be training data. But as long as you have a ground truth for each, then this is the paradigm in which things will work. Algorithms learn a function to map the input to the output. That is how we think about developing those. And that when teaching the algorithm to learn that mapping is what we call by training a model. You've heard of training data. You heard of training a model. This is what it's doing, learning that function to map input to output. And then we test it. We say, here is data that we did not give you in training. Can you give me the correct answer back, right? So supervised models. We've seen the Barrett's example, the Barrett's paper. In fact, all three papers, not all three, but the Barrett's paper that you've seen, we have the ground truth. We integrated Notebook LM, and the ground truth is the clinical diagnosis. And in this case, what we do is during training, the algorithm learns to map the input to the output, and it compares it with the ground truth. And if there is a difference between the ground truth, the mathematics of the model translates it into something called a loss. And the loss goes back to the algorithm and says, like the feedback we got, you're going too fast. That's the loss function. It came back to the algorithm. So the algorithm is learning, hopefully, and from the loss function, and learns a better function to convert the input into the output. This is supervised learning, right? If there is supervised, there must be something unsupervised. What is unsupervised? SAM is unsupervised. GPT is unsupervised. Cloud is unsupervised. No, not cloud. SAM is unsupervised. So in unsupervised, no, SAM is also not. SAM is in unsupervised, you don't have any labels. You just learn to cluster. Clustering is an example of an unsupervised technique, but you learn information in the data using techniques that do not need these labels. At the same time, because it's not learning any labels, you can't use it to predict a label right away. You have to do additional teaching to say, okay, this is how you predict the label. If there is unsupervised, is there anything else? This is weak supervision or semi-supervision. So we have this algorithm. So one algorithm predicts the labels. Some of them will be incorrect. It won't be correct all the time. But we take those potentially incorrect labels and we use that for additional training. So that's weak supervision. If we have the correct ground truth, that is strong, good supervision, strong supervision, but it's called supervision, not strong. when we have these predicted labels, it's weak supervision because some of them can be wrong. This is how GPT is trained. This is how Cloud is trained. This is how SAM was trained. The information is, there is information in the data, and the algorithm learns that information from itself. LLMs, the large language models, they were trained only to predict the next word. Given a sequence of words, predict the next word. Yesterday, you heard this phrase called context window. So given some information in the context window, predict the next word and keep doing it. And that's how they're beginning to change our lives. You just have to predict the next word. So if there are so many methods in AI, in the world of AI, what method is good for my research question? You came up with a ton of examples. This is not a comprehensive list. I want to say it out the bat. But we thought this would be something useful for you to take home, because it gives you a kind of a framework to think through. If you have X-rays, or if you have CT scans or images from the ultrasound, not videos from the ultrasound, just images from the ultrasound, or even images from the endoscopic video, just images, not the videos themselves, you would think of methods like a CNN, a convolutional network. You've seen segmentation of the pancreas in the US. That you would think of it as of using a UNet to do the segmentation. So there are two things that will influence what kind of machine learning model. Three things. One is what's the type of data you have, what's the problem you're trying to solve, and how much data you have. Those are the things that will help you decide which of these suite of machine learning and deep learning models you can use. If you have 3D images, MRIs are 3D volumes, you could use a 3D CNN, a UNet, or transformers, and so on. I won't read everything, but we know the last row. Sorry, not the last row. We have the tabular EHR data. That's where the regression comes in. I brought it back here to remind you that we can think of regression also as a machine learning technique. It's not too bad. And the random forest. The paper one Barrett's, it uses that. So that we can use that. When we have notes from the EHR, we can use LLMs. LLMs are we can also use them to analyze clinical notes. I think we're good to go.
Yeah.
So this is we didn't want to leave you with the activities out of context. So that's why we stole some of your time to bring you into the context. So we'll continue with, did you do 2D or 2C so far? Yeah, we're going to 2D now. We're going back to the notebook LM. Again, we're working with paper one, the paper on Barrett's. And this time we're saying, okay, now you have a model. Sorry, go on, Chaitanya.
Dr. Vedula and Dr. Akshintala, this is excellent. You're trying to put like all the AI like in half an hour. So a couple of questions before we move into the next slide. So for images, I understand CNN is something that you use, but for videos, you use a transformer model. Let's say if you're developing a model in esophagus, which is basically contracting all the time, and it's not a stable organ. And if I have images as well as video of like endoscopy videos, which one is better? Is it an image model that gives me more accurate information, or is it the video or videos gives me more accurate information? That's something that I'm curious about, because the image data is smaller. And if I have to use the same thing as a video, I'll be spending so much of storage. And also to analyze these two, it's a lot of computing. It needs a lot of computing resources. So which one is better, and what can I use, for example, for esophagus or also from pancreas standpoint?
What is the problem you want to solve?
Let's say I want to detect grading esophagitis and I want to detect early barriers. Probably I'll look into the work that I have
How
done
much
already.
data do you have?
Huh?
How much data do you, make up some data, how much data do you have?
See, we already have we are using a publicly available data set, so we have 3,000, probably like 4,000 images, which is quite small.
How important is to see some context window? So if I brought, let's say I'm doing the scope, I say, come in, you come in, you see, I hold the scope steady, you see an image on the screen, I say, can you diagnose esophagitis? Can you do that manually?
Yes, so.
Or do you need to see what happened, what's before and after that image?
I think that varies because with a snapshot, you can diagnose esophagitis, but with the image, I'm assuming that you get more data rather than a snapshot.
So,
with the video, I'm assuming you'll have more data rather than image.
We are grateful for you for bringing up this question because this is exactly a reinforcement of what we just discussed. You want to answer a question. So the three questions, so we said, what's the problem you want to solve? How much data you have? And is it realistic to imagine that with one image, you can manually do the diagnosis? What engineers will always say is, wait, to do this job manually, what do you need? They'll always ask that question because they want to know whether it's a problem you can solve with data because the humans can also solve it. Because you need the ground truth. If you can't do that manually, then I'm struggling with what's a good ground truth. I would start with images. In your case, I would start with images for the reasons you stated. You don't spend too much on data storage. You don't spend too much on compute to churn out these videos, analyze these videos. You need a lot of compute. And if a simple model can do the job, you don't need anything complex. So always start with the simple.
Swaroop, let me give you another example here. So instead of esophagus, I'm looking at the pancreas. I'm looking at EUS. And some of the endoscopists here can also maybe chime in. So if somebody gives me a snapshot, a picture of esophagus and asks me what is the grade of esophagitis, maybe I can identify structures and I can say. If somebody gives me a snapshot of the pancreas, sometimes I can say, is it a duct? Is it a vessel? I have to track, I have to look at before and after. So the temporal aspect of it, the time aspect of it is also important for me. So in that context, maybe video would be more helpful than a snapshot.
Yeah, but if you, like you said earlier, I agree. Any comments from the audience before you? I see gears turning.
The only question that I have is, let's say if I'm doing this work by myself or with a small team, will I be able to do it with videos, and assuming that videos are more, it gives us more information, but will I be able to achieve that?
Yeah, that's a good question. Videos in the case of pancreas ultrasound, they would always give you more information than one image, particularly to me, they're all just specks of black and white. I have no clue what's in it. I can't even imagine how all of you can actually see something there. It's hard for me to see anything. So videos would definitely give you more information. What you're asking is, but what's the personnel cost of analyzing more complex data? I would say, so think of it this way. Let's say I'm a primary care doctor and I wouldn't do endoscopy by myself. I would always send the patient to somebody who's competent to do it. So when every day I walk into School of Engineering as a medical doctor, I have not done any math in my life after my 10th grade. Everything that's engineering, I either find an undergrad or a grad student or a faculty and say, please talk to me about this engineering, how do you do this, and how not to do it. They have the competence. I learn along the way, but I rarely try things, I rarely take the initiative to solve these problems by myself. Working with a team is going to give you the best shot, particularly if the more complex the data. But if you have that, if you want to work with images, if you take cloud code and say, generate code for analyzing these images, as long as they're not a PHI and you're not putting PHI in a public domain cloud, generate CNN. I'm expecting that it'll do a great job. I'm sure some of you have already tried it. And our students they routinely use LLMs to help with coding. You can get a good code. The challenge will be to recognize whether it is doing what it's supposed to do. We can, because we have not seen enough of those. But students on the engineering side, people on the engineering side, when they see something wrong, they'll say that's wrong. Thank you. That was superb. We go to activity 2D. So now we're asking, okay, we've seen these models, we've seen them in context. Now, are they good enough? How do we validate them? So the prompt for 2D is saying, interrogate the paper to retrieve the sensitivity, specificity, AUC, positive and negative predictive values. Just mention it, that you have it. I'm not attempting to define sensitivity, specificity, AUC. I'm not going to teach you, but use the terms and just ask Notebook LM, what is the sensitivity reported in the paper? What is the specificity reported in the paper? That's all. So if you've gotten an answer, I put up what I saw manually, not my Notebook LM, but manually. This is what I saw in the paper. See if your answers by integrating with Notebook LM match these. Did anyone get sensitivity as 0.73? Yeah. AUC?
Yeah, AUC 0.91.
Yeah, there are multiple AUC values in there. One of them is for internal validation, one of them is for external validation. This is the internal validation. Yeah. I don't think the prompt doesn't say whether it is an internal or external validation. But these are the results for the internal validation part, right? And specificity 0.93. Do you see that number? Yeah. How about the positive predictive value? Did you interrogate, did you ask Notebook LM to retrieve or find the positive predictive value in the paper?
We asked, but I don't think it's not provided.
Did it say I cannot find anything, or it?
Yes.
It says the sources do not list.
Excellent. And my manual check agrees with that. And the same with the negative predictive value. Okay? So this part of the 2D was intentionally very, very short and very quick. So let's go to 2E. because there's a lot more to come, and what we have after the break is going to be much more exciting. With 2E, we're saying they used a bunch of clinical factors, clinical variables as input to the model. Some variables are more important for the model prediction than others. So we're asking NotebookLM to go into the paper and find out what method was used to analyze feature importance. So variable importance, which variables are important, with what method was used.
Going back to the previous thing, right? So if you have sensitivity and specificity, you should be able to calculate the PPV and the predictive value, right? So if you have the sensitivity, specificity numbers, I mean, obviously true, positive, and all that stuff, you should be able to calculate the positive and negative predictive values. So I'm just curious.
You'll need the marginal totals. So the sensitivity specificity gives you one margin.
Yeah.
You need the totals in the other margin to calculate the positive predictive values and negative predictive value. So it's possible, but if you'll need more information. So for example, you'll need information on the false positives and the false negatives.
Yeah. Thank you.
Anyone, what method was used to analyze feature importance?
So why is feature importance important? From a clinician, so I want to understand like how this model has come up with these decisions, because I don't want it to be a black box. So I want to make sure that I'm doing the right thing for my patient.
Yep.
So is that how you think when you are designing these?
Yes, primarily that was a conventional way in the world of statistics. People said include only variables that make clinical sense. Have a conceptual framework based on your understanding and include those variables in the model. Machine learning and deep learning, what they have allowed us to do is to throw the kitchen sink at the models. We can take everything in the patient's EHR and throw it into the machine learning model. But that's a lot of noise. We know that the length of my foot has no bearing on my risk of pancreatitis. But the length of the foot is a variable in the EHR, so it goes into the machine learning model. But what engineers feel, the engineers' conventional approach, default approach is to say, let the data and the model figure out which features are important, which variables are important. So this word features, I want to make sure, when we use this word features, we are saying it's the same thing as variables, covariates, factors in the regression model. They all mean the same thing. The default approach is to let the model training figure out which features are important. And you can use different techniques to control the model's direction. That is, when you control which way the model is training, which means which variables it's giving more weight and which variables it's giving less weight, when you control that, it's called regularization. But you use these kinds of techniques to say, let the model figure out which variables are important. It's good and bad. I'm happy to let it go, but I also come from a statistic background, so I say, let the model come up with what it wants, but then let's go back and see, why does something make sense? So then you get the benefit of both worlds.
So can you show some visual tools that we can use to understand the features?
So this is what you should have retrieved with NotebookLM. The method that was used is called SHAP or Shapley values. That comes from this. The graphical this information is peppered in multiple places in the paper. Did it bring it back as an answer to your question? What method was used? So, Shapley values is a game theory based methodology. Let's not go into that in more detail. You're not here for a machine learning course, but. So any more questions before I switch to the next idea? Please.
Just curious, how do you compare using SHAP value for identifying the importance of features compared to, for example, using random forest survival approach for features contributing to the risk of recurrence in, let's say, 1 year, 2 years, 3 years, and then doing out-of-bag predictors method and partial dependence of top predictors methods. Because I have seen a lot of debates between that and SHAP value. So, but the SHAP value is more commonly used. So I just want to see what's your comments on that.
Thank you. That's a great question. I'm glad you brought it up. This is only one of multiple methods. I do not think of, when we think of comparing different methods, at least for feature selection, I do not think of them as a statistical comparison. I think of them as a qualitative comparison. For a given data set, what does this give you? What does that give you? In terms of model prediction accuracies, or model prediction sensitivity and specificities, I don't like accuracies. And in addition, the clinical sense. What variables are being highlighted? Do they make clinical sense? I don't see those as, you can compare the AUC, the ROC plots between the two models with statistics. So that way you'll say, this method for feature selection gave me a better model than that method. You can do that. But in terms of, as long as the math behind that methodology makes sense, in SHAP values, the partial dependent, those methods, the math makes sense. So it's not a statistical comparison as the way I see it. So here, we want to go towards a break in about 3 minutes. So I want to do two things. Activity 2F, let's treat it as a bonus activity. We're not going to do that here. But the prompts are there. You've already answered this, did this exercise with 2D to 2A to E. Just try it out when you get a chance. The second thing, so Venkat and I, we want to spend a couple of minutes on this question. We've talked about all of these AI development, and you have data sets. We heard about a data set with images and CT scans and variety of things. How do you know when your data are ready for AI? In the sense, are these data good enough to train AI?
I mean, one thing that keeps on coming up is the volume of data, has been the theme here, because there's so much heterogeneity. Everybody uses a different type of endoscopy processor, variety of settings, patient variables, and so on. So that's something I often think about.
Yeah. Yesterday, there was a discussion about MRI images. MRIs are notorious if when the system changes, MRI settings change. And EUS is also, depends on the gain you set on the machine, the image quality changes. It may work out for you manually, but it may actually be heterogeneity in the data. So you need to think carefully through what data you have, how was it obtained, and how heterogeneous is it. And missing data. We all are very familiar with missing data. I'm not going to deep dive into this, but just that there are a ton of methods out there. Some of them are more, you would choose some of them more often than others. But you're also thinking about, are there missing data in my data set? When you say, is my data AI ready? And then this idea called feature standardization, you'll hear this, if you spend time with these papers, you'll hear this. The range of BMI goes from somewhere 10 to 15 to 30 to 50 something, right? But if you take the range of blood pressure, systolic blood pressure, it goes anywhere from 90 to 170, 160s. So systolic blood pressure, the scale is about 2 to 3 times the size from the values that you see for BMI. That is what is called difference in scale. When you have variables that are different in scale, some machine learning models are more sensitive to that difference, some are not. So depending on the model you choose, you want to ask, do I need to convert my variables so that all my variables are on the same scale from 0 to 1? Some machine learning models are more sensitive. So just putting that idea out. What else do you want to think about? Class imbalance. You have a lot of pancreas cancer. If you take 1,000 patients, a very small fraction of them have develop pancreas cancer. So that's class imbalance. You have very few people who develop outcome, a large number of people who do not have outcome. And these are just ideas to say, key ideas to say, to think through, are my data AR80? So let's hand it back to Venkat.
Thank you, Swaroop. And again, it's a lot of information. As we have seen, there's so much depth into it. And this only gave you a glimpse of some of the concepts that you need to think about and some of the nomenclature and terms that you come across in these manuscripts and how you can potentially use things like Notebook LM to understand these concepts better. So before we go into the next exercise, we'll take a 5-minute short break to stretch your legs, and then we'll come back and play around with some of the tools. Because there was a question about how do we implement this in practice, we will see that in the next activity. And you can see this URL in your notebook, in your handout. There is a website of a post-CRCP pancreatitis prediction tool. So there is a website, and then there is a password. So you can load that website and use that password, and we'll take a 5-minute quick break. We can share the slides later.
And then I'll switch back to you.
Absolutely.
Just for 1 minute. I just need 1 minute. You want to start? Okay. Now they just started talking even more. Everyone, I think we're going to come back to that last section of Module 3, where we will need to come back. So if everyone can get settled. We're only on the last few minutes of the boot camp, and this module 3, the hands-on, is going to end at 10:30, and then we're going to have a keynote talk on the future of AI by a non-biomedicine person who's amazing, and then we'll have a panel discussion with someone from Google Cloud as well. It'll be really great. This is a way to end outside of the box. And I just want to, I think there are several questions that came up, and I received several messages. So I just, before I hand back to Wincat and to Swaroop, can everyone download the materials? I just want to make sure you just have to have a Google account to download it. So you should be able to now have viewer access. Just make sure you have access. We'll send this as another email at some point, but this is one of the deliverables for the bootcamp. Module 1, Module 2, and now Module 3 should be on here. In addition, now you'll see photos. So photos from yesterday. So if you have photos that you want to share, send them to Nancy, or we can create a link. We can talk offline about that. But we'll post those photos, and then there's also the PDFs of the keynotes, including the keynote in about 20 minutes. So that way you won't have to take notes, and you get all this material. I know some of you have already sent all the materials to your labs. I know Jamie Solomon downloaded everything and sent it to her lab. So feel free to really publicize this information. The second thing is the brief survey. Please just, you received an email about an hour ago. If it's easier, just take this QR code and fill out the survey. And the survey ends, at the end of the meeting, so you can decide on just at least having it on your phone. And the last thing, as my last announcement, which is very welcome to many people who like to receive money, is that we had 16 travel awards, and I think some of you have not collected your travel awards, and that's Shuyun Zhang, Huan Hao Lu, Hao Jun Yu, and Hang Zhan Deng. And I apologize if I've not pronounced it properly. And so please collect your travel awards from me in the next, right now or in the next hour. And with that, I hand it back to our Module 3 chairs. Thank you.
Thank you. Thank you, Dr. Hussain. It's hard to compete with money, but we have a superb capstone to cap it off. This is based on Venkat's research. What we are going to do is we are going to, I'm going to set it up. This is a simulation of an activity in clinical decision making. Either you're seeing a patient or you're at your institution in a role where you have to make a decision whether a prediction model, an AI prediction model, is good enough to be used in practice. This is called PEP risk. For what you need, we'll just go to we'll listen about what is PEP risk from Venkat, and then we'll go to what you need and what exactly you're going to do.
Thanks, Swaroop. So again, topping off, and so we learned so much about how much effort we have to put in coming up with a prediction model, a decision-making tool. So now we will showcase a little bit on how to bring it to practice. And you can open this website that is there in the document. It's called Endoscribe PepRisk. So there is a URL in the document. You can click that, and then there is a password, endos-hop. So you can open that. We will also show that website to you. But while you're doing it, quickly to give you some background on post-CRCP pancreatitis and why we found it to be important, this is the most common complication of the ERCP, the endoscopy procedure. There are so many mechanisms involved in why one might develop the post-ERCP pancreatitis. And there are so many different prophylaxis or preventive strategies also. So mentally, it is very hard to predict what is the probability of pancreatitis after endoscopy, who do I admit after the procedure, what type of prophylaxis I should do, because they all have the cost and complexity component. And what we tried to do is we collected a lot of data because Swaroop asked me to collect thousands of patients' data. I sold everything I had so to get this data of 12 randomized controlled trials, 7,000 patient data. So these are all the different variables that we found to be important. But again, mentally, it is very hard for me to put all this data together. So then we used Swaroop's AI tools, and then we came up with a prediction model. On the left side, you see all the different variables, which are the risk factors, some patient information, some procedure information that we have all inputted into this prediction model and came up with the interface. So this is a calculator that we developed. So in this calculator, one can manually toggle and select and predict what is the probability of pancreatitis after the procedure. But this is something I have to do real time. I cannot drop my endoscope, open a website, and toggle some buttons. That's not realistic. So we also need to make it practical. And as Travis mentioned, so we have to make it like real time during the procedure. So how do I make it real time? How do I make it real time such that I don't have to leave my endoscope, open a website, and get this information right away? So what we try to do is use some other AI tools. So this is what would have been conventional. So this is a manual calculator, so where I have to go toggle some buttons. And what I try to use, ask Swaroop is, can I just speak it up during my procedure? Can I dictate, say, explaining like what I'm doing during the procedure? Swaroop, tell me, like, what would AI help me, and how do AI solve the problem here?
Thankfully, other people have built these models. So if you speak, we can transcribe it, convert it into text. And when we convert something into text, we have very, very good large language models, a variety of them, that we can use to analyze that text. So how can we use these two models to help you solve your problem?
So this is how we have developed that interface that you have on your website. If you open the website, you can see that speech-based thing. So first, I turn on my microphone during the procedure. I give it the patient information, and then I turn on the microphone and start dictating. So it records the procedure details. It captures all the things I'm doing as I'm speaking out. And it drafts the note for me, for sure, from all the information. But it also extracts the information specifically pertaining to the risk of developing post-CRCP pancreatitis. So it can do a variety of things. So that's what you can also play around. So it can write the note like this. So this also saves me so much time. So instead of me spending hours and hours in the endoscopy unit writing the note, it can do the note for me. And there is a tab that says PepRisk. So it extracts that information from my procedure, and it knows how many times the guide wire went into the pancreas duct, what type of sphincterotomy did I do, and so on. So it comes up with a prediction and understands it gives me a number for the risk of developing post-CRCP pancreatitis. And then I would decide, oh, this is too high of a risk of pancreatitis, so I would admit the patient after. And this is the prophylaxis I would do for that use for that patient. Again, this all comes back to how we can potentially use AI for like real time.
Thanks, Venkat. Yep. So this is the tool that he brings to you as a physician or to you as a decision maker. And this activity is in this activity, you're going to be that decision maker and figuring out whether this tool is good enough. How do you go through the motions to figure out whether this tool is good enough?
This is a simulated exercise. All of the data that you're going to use is fake. I made it up, literally made it up with R. So any of the answers you see about this tool is not a reflection of the tool. This data is all made up. What you're going to do are, the instructions are in the handout. You're going to activity 3. There is a spreadsheet called peprisk_simulated predictions.xlsx in the module 3 Google folder. You're downloading that spreadsheet, and I would suggest one person download that spreadsheet table, and another person, there are data on 10 patients in the spreadsheet. Each row is one patient, each column is one variable. What you're going to do is you're going to open up PepRisk, the website, you're going to log in, and for each patient in that spreadsheet, you're going to enter that data into PepRisk, and the second column of the spreadsheet is empty. I would say download that spreadsheet to your computer. Do not use it from the Google Drive directly. Download it. The second column is the predicted probability that you get from PepRisk. So you're going to plug in the information on one patient into PepRisk. You're going to get the predicted probability. You're going to enter it into your downloaded spreadsheet. Good? Please.
I'm very curious, actually. Can we automate this process, like with clause, say this is the website?
Yeah, you can.
And then we have the Excel file, just do it automatically.
Yes, you can. We didn't do it because our intention was to give you a chance to connect what you're hearing about AI with something practical. And we have Venkat's work giving us this platform to make that connection. But you can create agents to do that.
This is a question for Venkata. Why not going a step further and not just calculating the risk, but provide recommendations, give 2 liters of LR or place the stent, use tacrolimus, Any thoughts on that? Have you thought of that, of the next step rather than just a risk, which is helpful, but it's, or admit the patient, provide actual recommendations?
Absolutely. Thankfully, we were able to do it because we had so much patient data, over 7,000 patient data from randomized controlled trials. So here, it can also give you recommendation, as you can see on the screen, whether you should do indomethacin or IV fluid or stent.
Okay.
Then it says for each prophylaxis, what does the probability of pancreatitis comes down to. So there is also decision making. We do not have tacrolimus data yet, but as we get more and more randomized controlled trial data, we will be adding this information.
Fantastic.
Dr. Akshintala, a quick question. So this is a dictation tool, right? So is it inbuilt into the computer or like a desktop, or we should wear like a microphone? And the second thing is, not all the endoscopy suites are similar, right? So I worked with attendings who play electronic music. Some are very quiet. So, and also the staff surrounding you. So is there a noise reduction? And let's say if I'm playing a lot of EDM, does it affect the, your clarity?
Absolutely. The great points, very practical things, because we cannot do our procedures without our songs. So I did ask Swaroop the same question. So Swaroop, how do I avoid the background noise and people speaking and so on? So there were other methods that they were able to use to clean out all the background noise. So we were able to simulate this enough and test it in variety of settings, variety of background noise. It nicely filters out. And this is all things that are already there. Similar tools have been developed in the surgical world and so on. We just have to talk to the engineers and get the right methods.
So, but are we going to use that microphone, or is it going to be in the computer?
It will be a microphone similar to what you use, say, Abridge for clinical note dictation and so on. So there are some practical aspects. But moving forward, we are now going to use computer vision. And instead of me dictating and saying, this is the guide wire going in, it looks at the video and recognizes. These are all incremental stepwise. Again, solving some practical problems.
Sure, thank you.
Can I to understand how to interpret this, are we seeing that of the different strategies, fluid resuscitation plus indomethacin is the most protective, and then as you come down, least protective generally? Is that how this is categorized? Or
Correct.
does the order change based on?
Based on each patient's information, because as an endoscopist, you sometimes recognize that if I try to place a pancreatic duct stent, during my attempts, I cause more trauma.
Sure.
So that's the reason it might not be the best idea for that patient. But if the guide wire is already in the pancreas duct, maybe it's okay.
Okay. But generally speaking, it'll be listed with these 5 parameters in that order.
Correct.
Okay.
And this is constantly evolving as more randomized trial data comes in. It will be not just indomethacin, maybe diclofenac, maybe tacrolimus, and so on.
Excellent.
Yeah.
I just want to make sure all of you at the tables are able to get the predicted probabilities from PEPRISC. Anyone unable to do that exercise? There are 10 patients, it takes some time. So if one of you reads out and the other inputs it, then you can get the predicted probabilities more quickly for all 10. Is it working out okay for you?
I tried to do the automated thing, but
Did it?
the cloud says I don't have access to the website. Yeah. So I think the math is fine.
We don't have enough time. I think we should have given you more time to go through the other motions. But if you, there's more automation you can do. So I'll draw your attention back to us because we have another stellar panel session soon after this one. We don't want to keep you too long from it. So in the interest of time, what you have done is you said this is these are the patients in my clinic. I want to test this model against patients in my clinic. So you input the patient's data, you got the predicted probability, and because these are your patients, you will know what happened to the patients in the future, right? Once you follow them up, you'll know whether they actually had it. So you have a ground truth. You'll get a ground truth from your observations about your patients. In the spreadsheet that I gave you, I didn't give you do you see a column called the ground truth? Yeah. So I made up the ground truth. So now you have a column of probabilities. You have a column of probabilities in column B. You don't have enough time to complete all of them, but I think let's move on because I want you to see how do you actually make your decisions with this information. And the ground truth, you have a column of ground truth in column D. You can say, okay, how do you put a threshold on the probability, saying if it is less than some amount, some value, the prediction is that patient would have that outcome. And if it is more than that, the prediction is that the patient would not have that outcome. How do you determine that threshold? Typically, you go back to the paper to the original research that gave you that model. Most often, we say 0.5. But you're also allowed to fine tune that probability, saying, look, I want more specificity or I want more sensitivity. And you can fine-tune that probability to give you that optimal result that you want or optimal decision support that you want. In this case, let's say the threshold is 0.5. So if PEPRISC gave you a probability of 0.5 or less, 50% or less, then the predicted outcome is a 0, that the patient would not have acute pancreatitis. And if PEPRISC gave you a probability of 50% or higher, then you would say patient would have pancreatitis. Now you have a label, a predicted label. I added that. I did not, the predicted label is not included in the spreadsheet I gave you. But I added that in column C here when the probability that we got from PEPRIS is less than 50%. And here we see that it is not. And then I said, let's compare it with the ground truth. Let's compute the sensitivity, specificity, and more importantly, the positive and the negative predictive values. If using PEPRIS, we predict that this patient will have pancreatitis, what is the probability that they'll have pancreatitis? So that's a positive predictive value. So you compute those. I'm not going to teach you how you compute those, but if you want to, activity 2, there's another item called 2. You can try using Claude or any LLM to generate that code to say, give me sensitivity, specificity. Or you would work with a statistician. And once you have those, that is what helps you decide. When you go through this exercise, what you'll see are these numbers. You'll see a sensitivity of 20%, specificity of 1, positive and negative predictive values in AUCs. So these are the motions you'd go through to say, I have a prediction model, but how do I decide whether it is good for, whether it's good and ready for the clinic? Let me pause there. Yeah, sorry. One other thing, I can't help. Let me see if I can cover this in 30 seconds. May I? What you've done here is you have your sample. This is the testing data, the 10 patients you'd used. You evaluated it, and you computed your sensitivity or AUC. Let's talk about AUC. AUC, we can interpret it broadly as accuracy. 1 minus AUC is the error in the model. Right. But this error is in your sample. This sample of patients are not the only patients you're going to see in your clinic or your institution. You'll have your own population of patients you'll see in the institution. So whatever error you estimated or whatever AUC you estimated, it is an estimate of how this model will behave when you use it in all patients at your institution who are similar to the original patients used in the model development. It's only an estimate. So you always need some uncertainty around that AUC. If I come and say, hey, I did this and my AUC is 90%, we're good to go. Not really. If you ask me what's your confidence in that AUC, I say, oh, it's 0.5 to 1. It's a wide confidence, wide uncertainty. It's as good as a flip of a coin. If the confidence interval includes 0.5, it's as good as flipping the coin. So always make sure you also think about the uncertainty in that estimate. That's a statistician in me couldn't resist.
Thanks, Swaroop. Again, lots of concepts. There are some more bonus exercises like in the document. And any last burning question before we go to an excellent panel? Chaitanya? There's a microphone behind you, I'm sorry.
So very quick clinical question. So we were able to get to patient number 3, and the probability is 6.6, which was kind of low than what we anticipated because the trainee was involved in that case, and it's a young female. So our question is, did you guys consider the other lab markers? Because if a patient has a normal lab markers, and if you do ERCP in a young patient, the risk of pancreatitis is high, but I don't see those variables in the prediction model.
That's my bad. I made the data up. I did not put in any clinical sense into it. I just brought it from a random distribution. So it's all simulated data. Those data are not supposed to make sense, any clinical sense. They were just meant to help you go through these motions of doing this exercise. And this is how you would make a decision. Make sense?
But in the model, so this is the final version of the model, right? Or this is just for
The model is the final version. The Excel data are not.
No, but in the model itself, we don't have the lab values.
Yeah, I can quickly answer that. Yeah, there are many other variables, but we have to be selective. So that all comes back to the variable selection that Swaroop has talked about. That's a separate science altogether. We can have more discussion on that. But this concludes module 3. So hopefully you got a glimpse of the clinical prediction and how to translate into practice. So now I will hand over to Dr. Hussain for the panel discussion.
Thank you very much. Very hands-on. I know we took a short break, but I feel like maybe a 3 to 5 minute break would be welcome. Do I see nods? Yes, I see several nods. All you need is about 3 or 4 nods. So let's take a very short break, but then we'll come right back and we're going to end with a keynote and an outstanding panel discussion. An outstanding keynote and an even more outstanding panel discussion. So thank you. Please. It'll be the two. Oh, somebody took up a chair.
Oh, it's going to be 3?
It'll be the moderator and then the 2 on the panel. But first, he'll give a 20-minute talk and then he'll sit down. Yeah. And then when he goes up, when the panel starts, then at that point, can we put on that one slide for the Stanford AI Bootcamp in red?
The red one? Okay, the first one.
Yeah. So that way it sort of is easier for...
Yeah. I didn't see a specific panel slide. So
Just that opening slide. Perfect. What's that? There'll be 2 panelists and 1 moderator. Yeah. When he sends, he'll ask you likely to send an email, but then it's him. And then he'll take care of all of it. just, if you still have a problem, just email me.
Are you serious? Oh, that's not what I do.
Which one?
It's a JHR.
Okay, maybe. But let's ask Dr. King that. If it's still a problem, just email me again. And then I'll just speak to Shweta and we'll make sure.
Just only from AB, they need this stuff. Those who are joining. Okay, this is like.
Okay, perfect. Okay, yeah. Okay, great. Thank you for.
Oh, you just retired?
Now I know an answer to one of them. Now I know an answer to one of them. If I can get to it.
I don't have a question about.
Yeah. Well, then he would go up to Lake Casino. It's a big lake. Yeah. Well, there's Krishnagurti. Yeah. No, Krishna. Yeah, there's
Okay. And then you got your pointer. Okay.
Use that.
Okay, I think I said 5 minutes, right? What time do you have?
You want precise time.
Oh, yes, look at that. Okay. All right. You guys got a bonus. Instead of 3 minutes, we gave you 8 minutes for a break. But now we got to start up again. So please, if everyone can have a seat and make yourself comfortable, feel free to grab coffee, and there's plenty of orange juice, as you see. I think someone from our group really wants you to get the vitamin C. So please imbibe it before you leave. And it's my great pleasure to introduce our second keynote, the keynote for today, Mr. Faisal Suhail. And this is a real treat because Faisal is going to tell us about the future of AI, and I think he's calling it an exponential disruptor, as you'll hear. Faisal is a seasoned entrepreneur and managing partner at Presidio Partners. He focuses on deep technology investments. He's founded and scaled multiple successful companies, serves on the boards of leading technology and energy organizations, and his work is really his mission, as I've gotten to know Faisal, bridges advanced scientific innovation with real-world impact, particularly in AI, the life sciences, and sustainability. And so, please welcome Mr. Faisal Suhail.
Thank you. I'll take that. That's mine. Yeah, thank you. Won't even give me free water, but orange juice though. Pleasure to meet everyone, and thank you so much for inviting me. I am not a medical profession, so I will claim that right away. You guys are way smarter than I am, so I hope this will give you some, knowledge, because I already got all my medical knowledge I needed at dinner from Ashok. That pancreas is the most important organ in the body, and that's all I need to know. So with that, so we're going to keep this a little bit more interactive. I know we have a panel, but I'm going to try to keep it more interactive so we can kind of make sure people take something valuable from it. So before I start, I'm a student of history. So for a couple of thousand years, humanity did a lot of discovery. We found medicine, we found gravity, we did algebra, we did a few different things. But the humanity kind of stayed fairly static, about 500 million people on Earth. And then about 200 years ago, all of a sudden, we went to 8 billion, or towards 8 billion very quickly. Anybody wants to guess what caused that explosion? All the way in the back. Good guess, but not quite. It was the steam engine. The steam engine 200 years ago is what brought the entire replacing the human muscle with movement. So you can ship, you can move goods, you can grow things, you can have machinery, and that's really what changed the trajectory of humankind. So 100 years ago, so we're going to move 100 years ago, we figured out manufacturing. Model T, Ford, that ushered in a whole era of creating things, making things at a very large scale. That moved humanity forward by leaps and bounds. Labor value decreased, capital value increased because you could make factories and you can make product in factories. 50 years after that, you have this thing called the computer revolution. And that's really what started this everything that we're talking about here, personal computing, and then that brought in the internet and so on and so forth. And I was part of that revolution. I started at Stanford. My background is electrical engineering from University of Illinois, Champaign-Urbana. Then I came to Stanford for graduate school in electrical engineering, designing chips, VLSI, and then left to go start companies with my professor here, and then kept on building companies for about 17, 18 years, and then the last 23 years venture capital funding other companies. And while we were doing that, Jensen Huang, who created NVIDIA, was my classmate and my office mate. We actually started designing chips together in 1985, the same day we started our careers. So that was kind of an interesting beginning of what really happened, which is we started to capture data, and we started to actually utilize data. And now today we have something called LLMs that came out of being able to actually not just process the data, but first you have to capture the data. So a little bit more about the history of that. So with that revolution, there's a few things that are different from the previous three. This is really, the first three, we really started to replace the human muscle with machinery. Now we are really at a cognitive revolution. We're starting to replace this muscle, which Ashok told me is not the most important because pancreas is, but we're starting to now have a system that can reason, it can remember. More importantly, it can decide, which is something no system to date has been able to do. And we'll talk a little bit more about that in terms of what happened even this morning with Mythos and so on and so forth, which is the exciting part. And then you have a question of morality. Machines have never lied before. Now we're starting to see some very interesting behaviors. What's exciting that we're seeing from investment point of view and the entire trajectory of technology is not one single revolution. It's not the steam engine, it's not the factories, it's not the personal computer, it's not the internet. There's three very large trends that are coming together at the same time. It's AI, synthetic biology, and robotics, which becomes a manifestation of AI. So you're starting to see three trends come together at the same time, which is opening up massive markets. And the reason of my talk is AI. First, I called it an AI as an innovator. It's actually, I think it's going to be more of a disruptor. Definitely an innovator, no doubt, because it is innovating itself. But I think you're going to see massive amount of disruption coming from confluence of these three technologies coming together at the same time. I've heard CRISPR yesterday mentioned quite a few times, genetic engineering. We're seeing use of synthetic biology in creating new materials for energy capture, for carbon capture. We're seeing new applications of synthetic materials in new battery chemistries. So we are starting to see these applications, not just AI to do content creation, but we're actually seeing actual material science becoming a critical part of AI and synthetic biology. So I thought what would be interesting to do is compare the last big exponential revolution to AI. So I thought, of course, the first one is Moore's Law. Semiconductors started right here in Silicon Valley. 1985, the largest chip was 40,000 transistors, and I had the pleasure of working on that chip. That was the first chip that went into the very first AI computer, the thinking machine that MIT spin-off did. That was the processor, and I had the privilege of working on that design. 40,000 transistors. Moving forward, the latest chip from NVIDIA is 212 billion transistors, which is about 5 million times the density. That's your Moore's Law over 40 years, doubling every 2 years. Very simple, binary math, right? You double every 2 years. That's what gets you to 5 million. So I said, okay, well, that's been an amazing exponential leap. That is what's given us the technology to do what we're doing today. Now let's compare that to something called AI. And I broke down AI in tokens. Token is sort of the 3/4 of a word used to train an LLM. That's sort of the basic unit of both input, your question, and output processing, training the model. So I just use that as a metric for how do we think about AI in terms of its ability to be exponentially growing alongside semiconductors. If you look at the trajectory today, and I use 1 million tokens as sort of a metric, what can 1 million tokens do? Today, you guys were using Claude yesterday. 1 million tokens is about 40 cents. That's the price of 1 million tokens. That's what you pay. You pay $100 to Anthropic a month. You get about 250 million tokens. It's roughly about 40 cents a token. A million token is what you're paying for. If you look at that rise, that is, in the next few years, is already predicted to be 20,000 times cheaper. So the cost of AI is dropping exponentially faster than the cost of semiconductors in terms of number of transistors that you could put on a chip. So the reason I put this chart is very hard for humans to understand the exponential nature. We think, oh, doubling every year is not very much. A few years later, you're at 5 million times. But now we're doubling sometimes overnight. On AI, we're doubling sometimes. I wake up in the morning, you read the latest technology breakthroughs. Sometimes model cost or capacity doubles overnight. It's not 2 years. And that is the biggest difference that I see in our capacity to utilize this technology. So I said, okay, let's take 1 million tokens. What can we do with it? Let's look at a few different areas. What can 1 million tokens do for you? You can write about 7 to 10 novels worth of text, as long as you tell it what to write, which takes about a couple of years of best writers sustain writing. That's what they produce. Anybody wants to guess how long it takes to process 1 million tokens? It's about 4 hours. That's what our Claude model will do. It's about 4 hours. So in 4 hours, you can generate 7 novels. And I'll come down to the last one. You can write about 30 to 50,000 lines of code, real dense C++ code, and I've experimented this myself, which is about 1 to 2 top engineers, Stanford-trained engineers writing code from this building, CS building. That's what it takes. You can do that for 40 cents in 4 hours. That's the level of exponential disruption we're looking at, just to put it in context of what we're talking about. I thought cancer pathology was interesting given this crowd, so I actually spent a lot of time, and this is the latest data I have. I'm not quite sure. I've been able to validate it with certain experts, with certain companies that we have in this sector. One company called AI Doc, which is now the world's largest image capturing and giving you results on radiology. I think they already have 14 FDA approvals for different ailments, and that's just growing like leaps and bounds. So you can start to see that the amount of work AI can do in 4 hours with 40, 50 cents of investment is very different. So the question becomes, what do we do as humans? Where do we excel? What is the role for us? I mean, obviously, we're not going to disappear and go away, but what is the highest value product we can produce? And that's what we'll talk about. How does all this happen? The fundamental to all of this is data. And that's kind of an interesting story. In 1986, when we got the machine up and were running, the thinking machine, the hardware worked. We had no data to train it. We had no internet. We had no PDFs. We had nothing digitized. We couldn't really train it, even though the processing capability compared to today was very small, but still very hard for it to even recognize a picture because there was no data. It couldn't quite understand what it was looking at. But today that has changed. And I thought this slide is very interesting because of what's happening in the world today. Oil is stopped in Strait of Hormuz. Very similar to data, very powerful, but oil needs refining and processing. You can monetize it, but you need to ship it. Very dissimilar. And this is what I also saw from some of your talks that you've been talking about. It's unlimited in quantity. The really interesting thing about data is it becomes more valuable the more you use it. The more you have metadata, the more you tag it, the more you use the data, it gets more and more valuable because it has more information. And you don't need to transport it in any shippers or pipelines or anything. It's photons, and you have instant access to all the data in the world. And not just that, you can actually share the data very easily. So to me, data is the most critical part of AI, and that's the part that we were missing till today. Because given with what's happened with the internet, with PDFs, with digitization of all the information, even digitization of all the scans, that's the most important part. So to me, data is a fuel for next generation. By the way, I think there's going to be a lot of fights over data because that's the money. Each one of you personally, right here, you're producing tons of data. Somebody is monetizing it right now, right? It's not you. So that's going to be an interesting next fight, which is who owns the data, who monetizes the data, who secures the data, and so on and so forth. So be ready for that interesting discussion. It's started, but it's coming. So what's different about AI? So we've gone through this 4 mega trends, and in the last 30, 40 years, several micro trends, whether it's the web, whether it is the digitization, networking, so on and so forth. What's different about AI compared to those technologies? I would put it in 3 major categories. Autonomous innovation. Has anybody heard of Mythos this morning? Right? I see a couple of, very interesting. So we don't know exactly what's behind it yet, but Anthropic model is so strong that it actually figured out on its own where the vulnerabilities on all the security systems are, things that have been hidden for 27 years. It, without asking, figured out how to hack into them. And so we love to call that an emergent quality. Well, what does that mean? What that means is it's innovating by itself. I'm not asking it to do something. It's figuring out on its own, maybe I should do this. Now, no technology that humans have invented so far has that quality. It's a very, very different quality than anything humans have ever invented. As my son likes to call it, how do you raise a god? Which is interesting because it's starting to have emergent qualities, it's starting to think. Second thing is not just is starting to innovate, not just saying, okay, let me see how can I hack into things, well, I didn't ask it to hack into things. It's also thinking, but maybe I should hack into them, right? So it has autonomous decision-making capability. So how do you put guardrails? So that's going to be the big, big discussion around. And that's what I was glad Entropic sort of said, okay, they took the technology, they said, we're not going to launch it. They gathered the 40 most important companies in the world this morning, including JP Morgan, which has everybody's financial data in this room, to Google, to Apple, to AWS, and gave them the technology and said, go figure out where are all your vulnerabilities so they can be stopped before this is launched. Because if I have access to this model or you have access to this model, we can do anything with it. We could hack into any system, presumably. So that's the thing that is different about AI. And this is the most interesting one, self-preservation. Again, we've never had a technology that kind of says, how do I protect myself? And we've seen those, right? You've seen the email, I'm sure you've read articles about how it copies itself from one server to another. If you tell it, I'm going to delete it. This one just, we don't even know, for example, there's an interesting question this morning when I was reading some of the tech literature, that even the guardrails you put around a model, it knows what is being tested while it's testing itself. So it can just give you the answers when you're looking. It could be a quantum paradox, which is if I'm looking, I'll give you one answer. If you're not looking, I might give you a different answer. So these are really interesting qualities that we have never had to think about, to control, to actually design systems that take advantage of these, at least the first two, but not fall into the trap of the third, which is really interesting. So that leads me to, okay, so these are the capabilities today. So this is the massively multimodal reasoning model that we came up with. Stanford was involved in this, Princeton was involved in this. And it's 30 different domains, 11,000 questions, college graduate level students solving these problems, right? These are problems that are visual, they have images in there, mathematical equations, text-based. So there's 30 different domains, very comprehensive problems. The highest level graduate students, the top of humanity, scored at about 88.6 if they had access to the books to be able to solve those problems. Not access to the internet, but access to the books. As of December last year, we're already at about 86. And I wouldn't be surprised sitting here today, we've already surpassed the human 88.6 level. So what that tells you is the capability of solving not one domain, 30 domains across all problems. How can AI actually solve those? And these are, for example, there's a picture. One of the tests is there's a picture and there's a circuit diagram, no text. So it needs to figure out, look at a picture, figure out, oh, it's a circuit diagram, how to solve a circuit, what are the answers it's looking for, and it solves it. So you don't even have to even give it. I was a volcano plateau yesterday. I was sitting on Khalid's table, and it was good discussions about how much do you have to feed it? Do we have to tell it x-axis, y-axis, or is it going to figure it out on its own? No, it figures it out on its own. You don't need to tell, what data you want to plot how. So that I thought was a really interesting way to think about. Now, I think Stanford is involved. They're now coming up with a MMMU Pro, which is a more difficult set of problems. So the models can be challenged to solve even bigger problems in that sense. But this is real. So this is the question I get asked at most dinner parties. So I thought I would just put this up here. What should my kids study? Where's the jobs going to go? And you're seeing that. Oracle just laid off 30,000 people. Square, Dorsey's company, 50% of the company in one day. So this is no longer, oh, let me lay off 10% of the people, 5% of the people. I think I can optimize. These are cliffs. 50% of the employees go away in one day. And you're going to see more and more of that. I hate to say this, but it's clear because of what you can automate. So I created this scale. What's going to get automated first? What's going to get automated second, right? So definitely skilled trades will be the hardest to automate because you don't have robotic dexterity today. But it's coming. It's not far away. It's coming. But it's not there today. Robots can't get under your sink and fix your leaks, right? They can't get into your car and fix your leaks on your, oil leaks in your engine today. But definitely anything that has to do with you can click on your computer, on your phone, anything digital, anything systematic, that's gone. That's fully getting automated as we speak. And then education, leadership, judgment, those are going to be, leadership and judgment is going to be the hardest one and the most interesting one in terms of where I tell my friends how their kids should be thinking about the future, what skills they should acquire. Obviously, they should be technically savvy and understand how to use AI, but empathy and leadership and those skills will become more important than just learning how to code. Which is interesting. For the last 20 years, we've been telling all our kids, learn to code, learn to code, learn to code. You can get a job. Well, guess what? All of a sudden, you can't get a job if you know how to code because Claude just does it much better than any human can. But what to code is the most important. Actually, there's an idiom, right? Everybody knows this. In solving the most difficult problems, half the solution is being able to write down what the problem is, right? Other half is solving it. That's been humanity's go-to. I think that just changed. I would say the new thesis is 95% of solving a problem is being able to write down and understand what the problem is. 5% is going to be solving it. So that is really, really changing extremely fast. So if you can understand what to solve, what is the important problem to solve, solving it will be easy. So, similarly on education, I think our entire system is changing dramatically. I spent 16 years building Silicon Valley Education Foundation as my side project, and one of the key things we were doing there was taking more and more kids through sciences, math, and take them to college, make sure that they're on a college track. Now it's the largest organization of its type in Silicon Valley. But I remember the days when I was either a TI or looking for help from a TI, and you have to stand in line, and maybe you get a few minutes of time with your TA. Well, all that has changed. I don't need a TA. I have full 24/7 world's smartest TA at my disposal. I can ask any question and get those answers. Classroom policies have to change. Can you use AI? Can you not use AI? Is writing going to be an important skill, or is AI going to write for us? Those huge debates that have to happen. Back to my previous point, I think it's going to be more about applied problem solving, and strongest critical thinking skills are going to be the most critical parts of the future. How do you actually think critically about the problems, not just solving them? So I think our whole curriculum will have to change, and I'm looking forward to some of those interesting discussions. We tend to be very slow globally. So I think there's an opportunity. A friend of mine, their family owns a lot of schools, private schools, universities, and this is what I was telling them. You should be at the forefront of totally changing the syllabus and totally changing the way you teach. I know it sounds pretty scary, but I think that's what's needed. So here is what I see things happening. So task automation, we already know that's happening. Hiring shifts to less entry positions, we're already seeing that happening. Even Stanford computer science graduates can't get jobs. Unfortunately, the second step is you're also seeing happening in a massive way. Wealth concentrates in the hands of very few. You're either the infrastructure maker or you're the model maker, right? You're either NVIDIA, CoreWeave, those people, or you Google, Apple AI, and Microsoft and Meta. And what that does is trust in society erodes, right? Because now all the power shifts to very few people. It's not distributed. We already have been seeing that, but I think you're going to see a huge acceleration in that, and which is going to be interesting. And I hope we're able to manage it, and I'll talk about that a little bit. But being a venture capitalist, investing in AI, investing in energy, investing in different things, I thought I would just share with you. I'm not going to go into details. Happy to answer questions if you need to. But this curve is really, really interesting to think about in life in general. This is what happens. So this is the innovation trigger. This is where all the excitement comes up, where the new R&D, quantum AI is at the very beginning. You will have different artificial general intelligence is making it up here. This is where things get at the top of the peak of the hype. AI agents is right here, AI engineering, response AI, these things are here. Then we drop through what's called trough of disillusionment. This is where most companies fail, okay? So this is where all the excitement is. All the money gets invested right over here at the bubble. This is the bubble. Then we see, oh my God, that really didn't work. That was a great thesis. It didn't work. You go through and you have a lot of failures. And then out of there emerges a few things that change the world. And that has happened. You can take a look at this graph in any sector of any industry. This is just AI. You can look at this in EVs. You can look at this in batteries. You can look at this in computing. You can look at this in any sector, cybersecurity. So it's a good structure of, do you want to invest here? Do you want to invest here? Do you want to invest on these things that are coming out? Here is too late. You already built large companies, right? So OpenAI, Anthropic, they're already built. They're here. Now, if you're trying to invest in them in 1 trillion valuation, you're not going to make any money. If you got Anthropic and OpenAI here, which some of my friends did, they're good. A lot of us end up investing right here, and then we have a lot of bankruptcies, and that's just the way life works. But the goal is to find some of these companies out of this chaos, right? So let me paint a picture of 3 different paths. This is my last slide, and we'll open up to questions. And I think we'll have a panel discussion, Chris and I. So what are the possible paths forward? Okay, let's paint the nirvana path. AI does all the work, right? It can already write code. It can wash my dishes and find the robots will do all that. And we work maybe 10 hours a week. We spend a lot of time on the beach. We have time for creativity. We listen to music. We work on our relationships. That would be great, right? That would be a path. Very possible, right? That's a path I pray for. Or there's another path, which is automation without transition. See, humanity is very interesting metrics I was looking at. Each large technical innovation, guess how long the gestation period is? It's like 50 to 70 years. It takes that long for a technology. The cars came out, the horse buggies didn't go away. Day one, right? It took time. But then, obviously, at the end, every horse buggy went away other than the couple in Central Park in New York. But other than that, they're all gone. But you have time for transition. One generation retires, middle generation kind of gets up to skill, and the next generation grows up with it, right? That's all they know, so they're fine. This time, the difference is it's going to be 2 years. It's not going to be 50 to 70 years. It's going to be 2 to 3 to 4 years where you have a massive step function, which is, again, as humanity, we're not used to dealing with that. We're very slow. Humans are very slow in terms of how we progress. Sorry to say that, but we are. So this is sort of the maximum inequality. Productivity, rises, jobs lag, wealth concentrates in the hands of 7 people. We can name who they are. Trust erodes, and of course, when people have nothing to lose, instability grows. We've seen that, right? That's happened. Let them eat cake. That's the world that you can live in. Or you can have a very thoughtful next phase of automation as AI, reskill the people, productivity and wages rise evenly, and you have to adopt guardrails. Now, adopting guardrails is a very different task. So I was very happy to see Anthropic actually adopted some guardrails about 3 weeks ago when they said, let's not use this technology for autonomous bombing people, and let's also not let cybersecurity hack into every system. So those are guardrails. Now, the problem is we as humanity are not very good at sticking to those because the profit incentive is too high. If I don't do it, you will do it. If you don't do it, you'll do it. So I'm like, if you're going to do it, then I might as well do it, right? That's the rational or irrational mindset that we all have. So I hope we end up here. We definitely won't end up here, I think, just because that's not how. But my concern is we're going to lean more towards here. So our job as humanity is to keep this kind of more in this bucket. And if you're able to do that, this is an amazing technology that would really help humanity go forward. Anyway, so that's my talk. Hopefully I didn't scare you guys too much. So
Thank you, Faisal. Thank you, Faisal. That was brilliant. I would like to welcome you to join me for the panel discussion. And if you can join our panel, please, on the podium.
Sure.
And I would also like to welcome Chris Yang. He's a principal cloud architect at Google. He has numerous patents, and he focuses on cloud-native AI, and he focuses on security and practical applications of AI, so which is really very relevant for healthcare. So there will be microphones going around, and we will make this conversational. Please raise your hand so a microphone can reach you. Dr. Saluja, please.
Faisal, thank you. Very, very interesting. My question is not for science per se or medicine, which we are here for, but more of a societal change, what you are mentioning, and particularly concentration of wealth, which, as you know, in this country and many other countries in the world, but more so in our country here, is dramatically shifting. We already have big trends of wealth concentration.
Right.
You know, the lower 50% probably has 3%, and the upper 50% has 97%. I'm making up, but I think it's probably true. So, and if it's going to get worse, which that's what you're predicting somewhat, and that's probably true, then how would our society will continue? Wouldn't there be, French Revolution in next 10 years, 20 years?
Definitely, it's very possible, and that's why I think it's important to kind of step back. Our leadership needs to step back and re-examine the profit motive, right? I mean, what is the end goal? I think we get so, and I'm included in that group in the sense that our job is to create new companies, and of course the success is by them becoming multi-billion-dollar companies and so on and so forth. But I think having to step back and think about what's the end goal is a societal, question you have to take. I don't think it's an individual. I mean, individually we should all strive towards that, but I think we have to change that narrative, and we don't value the people who actually want to create that balance. We only value people that can create extreme outcomes. I mean, that's just societally where we are.
But what's the solution? What's going to happen? question is, would we have really
Look,
solution in 10 years?
well, look,
Societies will be,
look, I think,
society
look,
will be gone in 10 years?
No, look, there are two solutions, right? There's one that is top-down and one that's bottom-up, right? The top-down is government regulates, you put in regulations, you put in guardrails, you put in high taxation, and you see some of that being happening, right? Gavin Newsom introducing every billionaire must pay 5% tax, right? So that is a way to try to solve that, and the outcome is a lot of billionaire friends are moving to Florida and Texas, right? So that's not a national solution. That's like a very one-time, one-place solution. I think we need to educate the next generation to really be more mindful of how to build a society as opposed to just building a company.
Thanks, Faisal. A question to Chris. So Faisal has shared his vision on how things are changing. So you see more and more institutions and individuals getting onto the AI bandwagon. How do you think things would change in the next 5 to 10 years, especially in healthcare and biomedical research, from an AI perspective?
Okay, thanks for the question. It's a really hard question, to be honest. In the AI era, any kind of prediction or estimation for the next 2 or 3 years is going to be dangerous, right? If you look at what happened in 2022 when GPT-3 was announced, there was a lot of prediction. One of them is that, okay, the AI compute, the whole T-flop or flops is going to be increased like 3 or 4 times per 5 years, something like that. At that moment, I thought was, that's a joke. I'm probably going to venture capitalist kind of their hypes. No offense, by the way. But turns out you guys are right. So look at what happened right now. The total compute, I mean, AI compute kind of resources actually was maybe even tripled every year. Easily, we can imagine that you can see in the year of 2022, GPT-3 was trained on a platform with 10,000 V100 GPUs. That's roughly like 3.5 exaflops. But look at what happened right now. A Google TPU V7X SuperPod can easily just reach like 45 kind of exaflops. Maybe by the end of the year, the whole industry gonna have, I don't know, maybe 400, 500 kind of the zetaflops. We can easily reach somewhere around the utaflops probably next year. So that's a tremendous kind of progress for the whole industry. Okay. So that actually translated to some good messages for everybody over here. Like Faisal mentioned that the cost for the tokens gonna be dramatically dropped, which actually gave the opportunity to everybody that, okay, the AI can be fair. Everybody can use it. Everybody can do the innovation on top of it. So that's a great opportunity. That's probably a very strong kind of information for the next generation. They need to just do their innovative work on top of that, instead of just maybe follow it up, right? Just do some kind of legacy work. That's something I think I'm going to highlight in the first place. Second one, that if you look at what happened right now and in the next 5 years, and also I learned a lot from the event this time. Thanks, Professor Soho, for the opportunity. Actually, I captured a lot of information from all of you guys, the practice and what's the challenge, what's the blockers. A few things I want to highlight. The number one is the multimodality. I think Faisal also mentioned just now, a lot of people actually just mentioned the challenge when you try to capture some information from some docs. There are some tables, pictures, even videos this morning. Somebody mentioned that. This legacy kind of the models actually solve one piece of the problem, but now the large language model actually have multimodality by nature. They can digest the information from video, from audio, from the images, all the text, even some specialized waveforms from like a healthcare kind of machines, all sorts of stuff. I can put them together, have the kind of reasoning on top of that, and get the conclusion pretty quickly. That is something actually going to be progressing dramatically in the next 3-5 years. You probably can see that with the rising of the computing power and also the kind of sophisticated kind of reasoning behind it, the AIs can digest most of your kind of data in one shot pretty quickly. without any kind of the effort to break down the silos between the kind of the data modalities, without kind of the extra effort to just clean the data, all sorts of stuff. Yeah.
Thanks, Chris. That makes sense because multimodal is how humans think. When I'm making a clinical decision, I use my CT, MRI, endoscopy, and everything.
Indeed.
Not one piece of information. There are some questions from the audience, starting with a question from table 8. Keep it short, please.
Thank you very much for the great panel and great talks. So I'm personally in academic environment, and I'm planning to leverage AI first in research, in medicine research, and hopefully transition to industry. From your perspective as experts in both development of this technology and now trying to find the right companies or startups to invest on, what are the 3 main domains you see in the future that we should be looking for to focus as the future directions from academic and medicine perspective?
Happy to take that. It's I think look at the transition in terms of first is going to be things that are in the administrative, I will call it, which means anything to do with scheduling, charting, imaging, telemedicine. Anything in that domain is going to be the very first sector that gets really utilizes AI. I think the second is going to be the research. That's really where AI is extremely helpful, and we've heard from talks last 2 days, in terms of how much it can accelerate, how many research papers it can read, how even what Gary talked about, different drug interactions and developing. I think that's going to be the second phase. And then the third and the last phase is really going to be more the human interaction, the empathy, the doctor, the complexity of looking at a situation and how to take care of a patient or different types of drugs in different modalities. I think that'll be the last one. And you're seeing already, it's interesting, the world's first, and I've been waiting for this, the world's first probably multi-billion-dollar company by a single person in telehealth. It's Medvi. I'm not quite sure how you pronounce it, MEDVI. Single person, and then he hired his brother as one single employee. They did 65 million revenue last year. They're going to do 1.8 billion revenue this year. It's around GLP-1 telemedicine. Single person company. They have not, capital investment, $20,000. Never took a dollar from VC. I wish he had taken our money, but he didn't. Because he was able to use AI, 6 or 7 different AIs together to create that solution. So it was about figuring out what problem to solve, not how to solve it, right? So it's already happened. Actually, just a month or 2 ago, that it was announced. So ironic that it's in healthcare.
Yeah, thanks for the tips on where to invest, Chris.
Yeah, just add a little. This is an amazing comment from Faisal. I think given what Faisal mentioned here, I actually have a strong implication that everybody over here, including myself, should have a mindset of AI first, right? So based on my observation, a lot of people still treat AI as a tool or something actually far away from life or far away from work. But actually, yesterday, the keynote speech actually made a very good point that in the next stage, AI is going to be a co-scientist or something actually going to be a buddy, like shoulder by shoulder on a daily basis. If this is the case, what's going to be the behavior? What's going to be the mindset, right? Suppose you hire a new assistant, right? You wanted to just offload a lot of administrative burdens to him or her. So you're probably going to have step-by-step guidance to let her just ramp up in your work and help you just on some kind of, some interesting part in the research and create some kind of more innovative content over that. So that's been the journey, right? In the future, everybody's going to have a personalized AI. If you look at the open clouds over here, they actually penetrate into your life. Maybe you're going to touch tiny part of your work in your life. So what's going to be your reaction? So I think everybody, including myself, need to be prepared for that. Maybe start practicing and train your own kind of the personalized AI and find that kind of most sweet spot with guardrails, of course, with all the kind of innovative mindset, and create that kind of the co-scientist from day one.
Thanks, Chris, for highlighting what kind of AI skills we need to learn. It's a question from table 3.
Hello. First and foremost, thank you for the very nice presentation. My name is David Rutkowski. I'm an MD and PhD student from Karolinska, Stockholm, Sweden. I have 2 questions. You mentioned in your presentation that data is the new oil. If that is the case, then is it fair to assume that compute is the new currency? And if so, I also heard you saying that there was an increase in compute at Google, and you now have access to more exaflops in compute. What about for the local people around the world? Because it's great that compute is increasing for the hyperscalers, but we're also seeing a lot of price increases for technology and electronics, which are allowing compute at everyday local homes. So it's actually 2 questions. 1, is compute the new currency? And 2, is if the compute is allocating towards the hyperscalers, is it that in itself driving towards the inequality and wealth that you were also talking about?
I'll address the first one. I'll let Chris address the second one since it's about hyperscalers. So absolutely, compute is a new currency. And I'll give you a black and white example. So about a week ago, Jensen Huang, the CEO of NVIDIA, announced that he's going to give 50% of his engineers' salary in compute tokens. He said average engineer in his company makes $500,000 a year. So that is $250,000 worth of tokens per year. And he said, if you don't use them, you're going to have a conversation with me end of the year. Why didn't you use them? So now think about that. 40 cents is 1 million tokens. We know what 1 million tokens can do. $250,000 worth of tokens. I mean, he's happy because they're all gonna, money's gonna go to maybe NVIDIA's own data centers, but probably the partners, right? So it is absolute. He's not reducing their salary. He's giving that on top. So he's saying, okay, you make your cash and your bonus and your stock, but here is another currency, $250,000 worth of tokens. That's pretty earth-shattering.
Dr. Hussain, you have a comment or question? Or Chris, you want to finish?
Okay, the second question is really hard. Yeah, you're right. So basically, the hyperscaling kind of infrastructure now owned by only a few companies. I have to say so. And if you look at the current practice, I have to say that in the end, only maybe a handful of companies are going to do the foundational model training, like Gemini, like OpenAI, Anthropic, including Alibaba, a few of them. That's the truth. Right, for everybody like us, looking at all the hyperscaling kind of, the AI laws just growing like that, it's really hard for a small company or mid company, even human being, the individuals to just chase that. But we need to think of the whole thing from the other side. So basically, it's not a bad thing that how that companies actually have good ethics, actually do the kind of the foundational work. So they also build stuff like what happened right now is agentic frameworks, like everybody just automates all the stuff that's inspire kind of innovations. We just for the individuals like us, including myself, we just maybe jump on that kind of platform or that kind of era with a both feet, right? To start that innovation as an AI first mindset. That's probably going to be something that we get the benefit from that. That's do the innovation just to grow ourselves. Yeah, in the end, I would imagine that the whole world probably got a lot of infrastructure built here and there in the cloud, and for the individuals, you have all sorts of the tools or platforms or all the kind of AI channels to help you to do all the stuff like that. That's probably going to be the end. Yeah.
Thank you,
Dr. Hussain.
Yes, and this is a fascinating conversation. I actually had a question about collaboration and perceived competition in 2 states. One is between industry and academics. It's pretty clear from my reading that those 6 companies are all in industry, and academics has very little GPU in comparison. There's very little that academic institutions have in terms of the magnitude of computing. And so how do you see collaboration in this respect? And I remember yesterday Gary Peltz talked about AI co-scientist, which is, he didn't say it, but it's a Google company or a Google product that isn't released yet. That's one state. The other is countries. We think of ourselves as the most advanced in AI and technology. You mentioned Alibaba. When you look at the AI index, the human AI, sort of a Stanford HAI annual index, it shows how China has surpassed the US in various aspects of AI, while the US maintains a lead in perhaps the larger segments. Can you each comment on the importance of collaboration with industry and then between countries?
I'll comment on the collaboration. I think each one has a very distinctive role. I see the research as really setting the guidelines, the data, the methods, the methodology, and how to go about utilizing all of that. And then I see industry actually providing the compute and doing that work. But I really do see if research can work closely with industry to create those guidelines and create the data sets and create the methodologies, industry will adopt those, because I think research is much better equipped in doing that than industry is. But industry is much better equipped at scaling, and providing the compute. That's how I would look at the partnership.
Yeah, I agree with the collaboration part. So if you look at what happened in those 2 days, I was sitting there looking at all the kind of prompt outcomes over there. I watched all the people just sharing the content is good, bad, very kind of complete, reasonable, all sorts of stuff. To be honest, I have no idea about that. I'm not an expert in this field. So that's actually gave a strong hint to this conversation that for the big companies, they have the hyperscaling kind of infrastructure. They have all the computational framework, all sorts of the kind of tools and surroundings, but they don't have the domain knowledge, right? They need to rely on the academia in the different verticals to feed that type of data, knowledge, practice, experience, all sorts of stuff into this kind of collaboration. And in the end, they're going to have a very sophisticated or well-calibrated kind of the AI tools or models for certain verticals. Very good example is that like a Google kind of DeepMind built the MED LM, right? That's it. Originally, they are MED Palm, then evolved to MED LM, LM kind of hyperscaling, a lot of good kind of healthcare dedicated kind of models. The use of specific kind of healthcare kind of the data and input a lot of kind of knowledge over there and create that models actually to help the healthcare specialists to just grow their kind of the usage. That's a good example of that, right? I think the second question is probably beyond my knowledge. Is superpowers in the world who own a lot of AI infrastructure, AI models, AI practice? Well, in the end, like Faisal said, is a bit kind of regulation that is needed, right? Secondly, is that the super companies behind it need to have that kind of initiatives to just have the fairness to let everybody use AI, right? Right. That's something actually Google has been doing. We have that foundational kind of so-called secured foundation of the AI usage, SFAI. That actually gave that kind of principle to everybody in the Google to every build stuff for everybody. Not something actually for a specific superpower, or not something have to be, somebody own the kind of infrastructure. No, that is something actually is the responsibility of all the major kind of the superpowers, especially the AI companies, to just follow. In the end, they're going to benefit the whole industry or whole society.
Thanks, Chris. Since this is an APA-sponsored meeting, let me ask you a question from a pancreas perspective.
The most important
outcome.
Ashok said that.
And you saw previously Swaroop mentioning 14,000 medical products going through FDA approval. And only a fraction are in GI, none in pancreas. Couple of questions to you both. One from an investor perspective. A lot of investment into tech, med tech, but how do you look at say, for example, pancreatic disorders. That's a much smaller market. And how do you perceive how FDA looks at this AI? And what are the changes coming up in AI from FDA perspective? And to Chris, similarly in healthcare, we are so much worried about security. FDA is also thinking about security. So how do we address these bottlenecks so from an academicians so to push the field forward?
Talking about security part, okay. Just now we have that kind of privacy conversation as well with the audiences. That's a very, very severe kind of the challenge right now. So we have a few findings. Even though that we take all the effort to protect the data, protect all the AI infrastructure over there, they still have a risk, right? So the AI companies actually spend a lot of effort to self-prove that this one is safe, this one actually have some, guardrail the protections over there. Based on my experience, that never be enough. So now the industry have some new innovations. We call it confidential space, or we call it the zero trust kind of the computing, which means we create kind of enclave based on the theory of the confidential computing, and put the models, all the data in there, and then shut the door, including the data owner, model owner, infrastructure owner. Nobody can touch it. So this one, by theory, that we don't have to prove that we are innocent, because the model or the theory itself proved that nobody actually can touch that. That's something actually have already been done and applied to some field. As far as I know, that the U.S. government and also some kind of big banks or some kind of highly sensitive kind of industries already adopt these technologies, run their kind of AI with the state-of-art kind of models in there. That's number one. Number two, I think the guardrail mentioned by Faisal actually going to be extremely important. But how to apply the guardrails going to be extremely sensitive. That actually needs the whole industry to follow some kind of some responsible AI's way. I think one good example I already mentioned that Google have done, and another good example is the methods. The methods actually mentioned by Faisal this morning. I think Anthropic did a really good job because of their strong capability of methods. They initially opened the model to some like government, big banks, or some like healthcare kind of the owners who actually own a lot of sensitive data. So let all those guys use the methods to just do the scanning of their infrastructure and also software and find the vulnerabilities, make sure they can just strengthen their kind of security protection and patch all the kind of vulnerabilities before they open that model to the public. That's extremely important, right?
The only thing is we don't know if Metos is going to tell the truth.
So that's the kind of joint effort, I would say, right? That's actually have a lot of funding from the company. They actually, feed out the kind of the information to all the kind of the, organizations who own the critical infrastructure. Then they just gradually patch or improve the security bar of that before they open to the public. Maybe, like some kind of underground economy, some hackers probably going to use the same type of the AI to do the similar things reversely, right? Reverse engineer a lot of stuff. So that's all good examples of that. Maybe we don't have an ultimate solution at this moment because AI is evolving quickly in different verticals. We may just encounter very challenging questions or some very challenging situation, bottlenecks. But as long as I already have that kind of ethical kind of guardrail to say, yeah, let's face the challenge together. I believe that we're going to have solutions step by step and just always have that compete with the kind of underground economy. Turns out that going to be safe in the end.
Venkat, I'll just quickly answer your first question. Gary talked about this yesterday, right? This is a huge problem. 12 years, 2 billion, and you either get a 0 or a 1. And that's a pretty hard problem. And we've been dealing with that for the last 30 years doing this. So when we look at these diseases, there are two categories. Either you have a massive market where you have a solution which you can, whether it's diabetes or fatty liver or something of that nature, or you have an orphan disease. So we look at it in those two categories. If we're going to come up with a solution, spend $1 billion in 12 years, either it has to pay off in terms of an M&A because there is an orphan disease and you can get a lot of money from a company that's going to buy you, and we've been very successful in that. Or you're going after the big gorillas and you're creating a drug in the middle of a massive market, and that just takes, you better have a real, good candidates for, the drug at the end of the day. And now we do use AI to figure out different molecules and what has a better probability and so on and so forth.
A final word from an FDA perspective.
From FDA perspective, again, it's like the similar thing, right? I mean, FDA AI, there's a whole division now in FDA that is looking at AI. But for us, it's really about how to design the trials in such a way that we can manage them, get them through the trials quickly. Smaller trials are better because for us, the bigger the trial gets, it gets extremely expensive. And the outcome is still very binary.
Thank you. I mean, the current FDA commissioner is a pancreas surgeon. Some of you might already know. So we'll get a little bit more favor, hopefully. But thank you both for the brilliant answers. I'll pass it on to Dr. Hussain.
Sure.
We have to give you something. Oh. I would just ask Dr.
A pancreas, a new pancreas? No.
I would ask Dr. Saluja to also come up, please. And on behalf of the American Pancreatic Association, we'd like to recognize.
Oh, wow.
Great. And the first is, let's see, to Chris Yang, and it states here that it's presented to Chris Yang in grateful appreciation of your distinguished contribution as a guest panelist at the APA AI Bootcamp at Stanford.
Thank you, sir.
Let's get a picture. And Basil, you also come in the picture.
Oh, sure. Why don't we give 1 to 5?
Yes, yes, and then we're good. Okay, great, cool. Okay, now we're going to do another picture. And Chris, we're just going to switch here. And this is presented to Faisal Suhail. I like your last name.
Oh, yeah.
In grateful recognition of your distinguished contribution as a keynote speaker at the APA AI Bootcamp at Stanford.
Oh, thank you so much.
Okay,
right.
thank you.
Well, thank you so much.
Such an energizing session. And we are. We're already getting them for LA. Ashok is already getting the process started. So we are nearing the end. Some of you have to catch flights, and so if you needed to leave, please know that there's a to-go lunch. So we want to make sure you're fed before you go, so you can take it on the go. But we will have just about 20 minutes of wrap-up. And the very first is that Dr. Venkat Ashkantala, as co-course director, will give us just a 3-minute summary of the highlights of the boot camp. And then after that, we'll just have a few closing remarks, and I would, at that point, ask Dr. Saluja to just close the session for us before 12 o'clock.
Thank you, Dr. Hussain. And again, all of us have seen that AI is already here. And this is a workshop, so we were able to look at all the tools that can be used in AI. We got to use those tools in practical aspects. We saw that AI could be used in a variety of applications, in clinical decision-making, drug discovery, and on and on. We are not trying to make you all data scientists, but we are all trying to have you ask the right question to AI. And ask AI, is this the right type of data? Will I be using this AI in my patient, and on? So that is all we are trying to help you all understand. And we see a lot of future promise, and a lot more we have to learn. So we saw there is so little fraction of AI applications, especially in the pancreas world. So we are thankful for APA to help us do this workshop and get us all more into AI. We also learned that AI, thankfully, would not replace clinicians or scientists, but it would be the clinicians and scientists who know how to use AI who would be leading the field. So these are some of the things we learned, and there's a lot more to learn. So there are more courses and workshops from APA on helping us how to learn AI. So these are some of the things we learned from the last 2 days. Dr. Hussain?
Thank you, Venkat, for those highlights. And I would ask Dr. Saluja to please come up and offer a few concluding statements just as we end. I have the chance to, again, just reiterate some of what I mentioned at the opening. And one of them is that we want you to go away with something in hand, at least virtually. And so hopefully you found this interesting. The materials are all available to you. Publicize them widely. Take them back to your institutions and tell about what you learned, and especially to other trainees. There's a survey. You saw an email about the survey. Please, even now, feel free to start working on your survey, because now we've got all the information for the survey. The question is, should we do this again? And if so, what would be most important to you? Then there were actually about 25 awards. Some of them were to Stanford trainees, and so they didn't receive a travel award per se, but the APA was very generous in providing quite a bit of subsidy to about 25 trainees, 16 of whom received fairly sizable travel awards. And only all of you, other than 3, have taken advantage of it yet. So if you're in that 3 category and just haven't picked up your travel award, please do it before you take off. Otherwise, Dr. Saluja.
I will take them for sure.
Yes. We'll use it for his next vacation trip. And again, for me, a thanks to so many people. I want to recognize, to start with, our hosts, the Stanford Pediatric GI Division. I've heard so many comments. It means so much to me as a division chief to hear that we've got an excellent team. I could not agree more. I want to again thank Coralia Sianga, Nancy Tran, and then, of course, our other staff members who jumped right in and were present with us throughout, including Ash and Sam. So let's give them a round of applause. And I also would like to just, if we can acknowledge and thank and applause the AV team, Nathan and Eric. You both did a great job, so thank you very much. And of course, as I give the microphone to Dr. Saluja, we wouldn't be able to host this without the sponsorship of the APA. The APA spends a significant amount of its revenue towards the annual meeting, for trainee awards, grants, a very large amount, proportionally much more than most organizations would ever consider, and now these inaugural types of meetings. So let's really give a round of applause to the APA and Dr. Saluja for the sponsorship. And of course, my co-director, Dr. Ashkantala, and long live Hopkins as well. So thank you very much.
I hope all of you really enjoyed and learned from this meeting for last day and a half. I don't know about you, but I did for sure. I think it's been a great learning experience for me. I really didn't know much about, I knew AI, obviously everyone knows AI is going up and making a lot of money, not for me, but for everyone else. But it has been really great learning experience. I learned, hopefully it will make my life a little bit easier going forward. And all of this would not have happened if it was not the ideas, and I'll come to that in a minute, but before I go there, I just want to thank the team first, right? Venkat, you did an amazing job, man. I don't know how you find time, because whenever we call, you are not there, but you still spend so much time and effort for that. Right? Maybe you worked from Tibet or from wherever you were, but you did amazing. Thank you. On behalf of APA, I really appreciate what you have, done for this. And of course, I want to take a minute to thank the team here, and that's not you, Suhail, it's Cornelia, Nancy, Ash, all of you have done really amazing job. It's a lot more than I expected, and particularly I really, really want to appreciate Nancy. Where are you, Nancy? Can you stand, please? Where is she? I mean, Nancy has done an amazing job. Given that she's going to be second-time mother in next 2 months, I hope not too sooner, and she's been just taking care of everything. Millions of calls with her and helping Suhail and Cornelia and Shweta in Miami. So she has done really amazing job. So thank you. Thank you, Cornelia. Thank you, Nancy and your team. So I think the whole idea of this boot camp, I think started about 18 months back when Suhail, not you, sir, Suhail became president-elect of APA. In APA, the way system works is that you are a counselor for 3 years, then you become president-elect, president, past president. So that's kind of our system. And it's been going on and successfully for 50 plus years. So when Suhail became president-elect, so he and I sat together, I think we were in Hawaii for our 24th meeting, and we said, okay, so what is the big thing? Suhail is always a, big idea guy. He doesn't worry about small things, right? So he said, you know what? We need to talk about AI. We've been talking about machine learning and radiology and those kind of talks, but we never had something in AI. And he says, and I said, great. And he was taking a sabbatical at that time to learn and join classes to learn about AI. So it was perfect timing. So we decided, great. And then over next 12, 16 months, the ideas developed more. We sat together in China, and I think we were in Chongqing when we met again, and then we discussed this in Shanghai and other places. And that's what it ended up. So we decided we will have a boot camp here in Stanford, Mecca of AI right now. And then it's for more young people. But then we will continue this for broader audience. So we are going to do this, learn from this, and improve and do better if there's anything like better. But AI always learn, right? I mean, that's what you guys were teaching, that everything you do, the next thing will be more precise. So we're going to have a big meeting in Los Angeles on December 9th, whole day of AI in pancreas. And I think it's going to be very interesting. Suhail is already, spent a lot of time planning for that, and it's going to be very, very successful. So I really want to thank Suhail, Dr. Hussain, for organizing that and leading our organization. I mean, I have worked with many presidents, and I think one of them is sitting behind right there. Dr. Min, stand up, please. Min has been our really president, and now he's international relations counselor. He just came back from Shanghai, last night at 11 p.m. and just came to this meeting. So thank you, Min. But Suhail has really, he's very initiative, obviously very hardworking, and he believes in big changes. So I had a pleasure of knowing him when I used to be young. But imagine when I was young, how young he would be, right? So he was a GI fellow at Yale, and that's when we met and we worked together for, some of the things when he was working with Fred Garlick, another amazing pancreatologist at Yale. And then he moved from there to Pittsburgh, and I had pleasure of visiting and staying at his home in Pittsburgh. We became very close friends. And I knew he's going to make big changes to both APA, but more importantly, what he's doing at Stanford. I didn't even know that pediatric GI could be that big deal. I mean, I thought they're like, pediatric patients are between 0 month to 18 years, right? Whereas we adults are from 18 years to 98 years. But his GI, so to me, the GI division should be proportionate, like it should be on an average 1/5 of what the adult should be. Logic, right? I mean, AI logic, right? That it should be. But he developed this division in last 6 years, from 14 to 36. And he tells me that he has 10 more openings, so I'm going to apply for that, right? But really is great. I think APA is much better organization because of you. And we really, really appreciate and looking forward to working with you for our main event in December in Huntington Beach, Los Angeles. Thank you, Suhail. Really proud of you.
Thank you for those kind words.
No, thank you. I guess this is the end. Well, all good things have to end. But please make sure you grab the lunch, because one way or the other you paid for it. So don't let it go waste. Thank you. Thank you. Thank you.